Hi, welcome to my presentation on Chapter 2, the Chemistry of Life. So you might not have figured there would be chemistry in your biology class, but actually biology is basically, it's based on chemistry because organisms are made up of molecules. So we don't cover a lot of chemistry in here, but we will cover a little bit. So we'll kind of start with a really basic overview of some basic concepts in chemistry. First we have atoms and elements. An element is a pure substance that cannot be broken down into simpler substances using ordinary methods. So maybe you could do it if you had access to nuclear fission, like what you have in the heart of a star. But if you're just limited to, energy sources that are naturally occurring on Earth, then you can't break an element down into a simpler substance. Elements are made up of atoms. And in any sample of a pure element, you're going to have atoms that are all belonging to the same, that are all the same type of atom. They all belong to that element. So an atom is the smallest unit of an element that still has all of the same characteristics and properties that the element has. So if you were to break an element into literal, like smaller and smaller pieces, eventually you would break it into atoms, and at that point you couldn't break it down further, or if you did, that would require, not ordinary means. That would first require like extreme energy sources, and also the result would not be, units that have the same properties as the overall element. Within organisms, you have four most common elements that you find. They are hydrogen, carbon, oxygen, and nitrogen. So out of all the many atoms in your body, most of them are hydrogen, carbon, oxygen, and nitrogen. Actually, 96% of them belong to one of those four elements. Out of those four, the most common one is hydrogen. Then you have carbon, and then oxygen, and then nitrogen. So those are listed in order from most common to least common. Then for the remaining 4% of the atoms in your body, they are accounted for by like a lot of different elements. Actually, 3% are phosphorus and sulfur, and then that last 1% is a bunch of different kind of trace elements that you have. So that can be sodium, chloride, potassium, magnesium, zinc, iron. Those are just kind of the most common trace elements that you have, but you also have other ones as well, like manganese or selenium. There's a bunch of trace elements that you have in your body. So you're 96% hydrogen, carbon, oxygen, and nitrogen, 3% phosphorus and sulfur, and then 1% a bunch of stuff. Organisms, including you, of course, are always made up of organic molecules for the most part. You also have some inorganic molecules, but most of your molecules are organic, which just means that they are based on a carbon. So organic molecules will have like a skeleton that's made out of carbon, and just carbon atoms that are bonded together. And then you can have other elements, or atoms of other elements kind of stuck onto that skeleton. Like you would usually have a bunch of hydrogen atoms kind of sticking off of the skeleton, but you could also have oxygen or nitrogen or phosphorus, or a bunch of different things. So that means that organic molecules are not necessarily made by organisms. They can actually be made by inorganic processes as well. And they're also not just defined as the molecules that make up an organism's body. They're just molecules that are based on carbon. So in chemical evolution, we would have had to generate organic molecules from inorganic molecules, basically, and it couldn't have been done by organisms. It would have had to have been done by, inorganic processes. So you would have started with like really simple inorganic molecules that do contain carbon, like carbon dioxide, and you would need to have some way of sticking them together to make organic molecules and then more complex organic molecules. So if we look closer at an atom, you actually can break an atom down into smaller particles, but those particles do not possess the same properties that the element that the atom belongs to has. So there's three basic particles that you have inside every atom. They are electrons, protons, and neutrons. Well, I guess I should say almost every atom will have like all three of those types of particles in them. The electrons are the very, very smallest ones, and they are negatively charged. Protons and neutrons are about the same size as each other. Neutrons don't have a charge, though, and protons have a positive charge. So they're actually called protons because they have that positive charge. Electrons are actually a fundamental particle, which means that you cannot break it down into a smaller particle, no matter what energy source you have available. But protons and neutrons, which are much bigger than electrons, actually are not fundamental particles. So that means that if you do have, an extreme energy source available, you could potentially break them down into even smaller particles called quarks. But that we don't really need to get into too much. The protons and neutrons will always be arranged kind of in the center of the atom, forming the nucleus of the atom. And then the electrons orbit the nucleus, kind of forming like a cloud around the nucleus. So in the diagram here, that's kind of showing that you have in the center the nucleus made up of protons and neutrons, and then you have the electrons orbiting around the nucleus. A lot of the time we show the electrons as orbiting, as though they have these set paths that they follow around the nucleus, and they just kind of orbit around the way that a planet orbits a star, or the way that the moon orbits the Earth. But actually it's not quite like that. The diagram on the bottom is more accurate. So in the very, very center, you have the nucleus, which is zoomed in on here, so you can see the protons and neutrons that make it up. And then around the nucleus, you just have this kind of cloud, which is where the electrons would be found. You actually can't know where the electrons are at any given moment, necessarily. So you just have this kind of cloud of places where you could expect to find them. And the darker the cloud is, the more likely that you would find them there. So you're more likely to find the electrons in this particular atom closer to the nucleus, but you could also find them further away, potentially. In general, atoms will always have an equal number of protons, neutrons, and electrons. So for this atom right here, it has 2 protons in its nucleus, also 2 neutrons in the nucleus, which means you should find 2 electrons orbiting in this electron cloud. The only exception to that rule is hydrogen. Hydrogen is the simplest element and the simplest atom. It only has 1 electron and 1 proton, so it actually doesn't have a neutron at all. Other than that, all atoms have equal numbers of electrons, protons, and neutrons. The elements or atoms of all the different elements can be kind of organized into this table called the periodic table. And they're just kind of listed in the table in order of increasing number of protons that they have. So the first element that you have there is hydrogen, that just has 1 proton. Then the second one is helium, that has 2 protons. Lithium is the third, that has 3 protons, so on and so forth. So all of the elements that we know of are listed on the periodic table. And elements on the periodic table have 3 different numbers that are associated with them. You have the atomic number, the mass number, and the atomic mass. The atomic number is just the number of protons that the atom has. So for instance, for carbon, which is the basis for organic molecules, it has 6 different protons. It is the 6th element on the periodic table, and so its atomic number would be 6. Then you also have the mass number, which is the protons plus the neutrons in an atom. So it's basically how many particles are inside the nucleus of the atom. For most atoms, unless it belongs to hydrogen, then the number of neutrons will be the same as the number of protons. So for carbon, if you have 6 protons, that means you also have 6 neutrons, and if you add them together, you get 12. So the mass number for carbon would be 12. The only exception to that rule, again, would be hydrogen, which doesn't have a neutron, so its atomic number is 1, and its mass number is also 1. Then you have the atomic mass, which is the actual mass of the atom, measured in daltons. A dalton is really small. At the bottom there, you can see the conversion between 1 dalton and some fraction and some tiny fraction of grams. So of course, you don't need to know that conversion, but just know the dalton is real small. A Dalton is actually defined as 1/12 of the mass of a carbon atom, so that means that carbon has to be 12 Daltons in mass. Since the Dalton is 1/12 of the mass of a carbon atom, and a carbon atom has 12 total particles in its nucleus, 6 protons and 6 neutrons, that means that 1/12 of that mass, or 1 Dalton, would be the same as 1/12 the number of particles it has in its nucleus, or 1 proton or 1 neutron. So a Dalton is about the mass of a proton or a neutron. So normally, an atom would have equal numbers of protons, neutrons, and electrons. Unless it's hydrogen, then it doesn't have neutrons and it just has a proton and an electron. But for normal atoms, except for hydrogen, it's always equal amounts of all those 3 particles. If you start changing the number that you have of one of those types of particles in the atom, then you're going to change something about the atom. So if you start changing the number of electrons in an atom, you're going to end up with an ion. An ion is an atom that has a charge. For most atoms, or for normal atoms, you'll always have the same number of protons as you have electrons. Since they have opposite charges, the charges will kind of cancel each other out, and if you're looking at the overall atom, it will not have a charge. Since it has equal numbers of positive and negative charges, overall it doesn't have a charge. But if you start adding electrons or taking electrons away, now you're going to end up with a charge. If you added electrons, then you're going to have more electrons than you have protons, which means overall you have more negative charges, and you end up with a negative charge on the atom. If you lost electrons from the atom, then you're going to have more protons and less electrons, which means more positive charges, so overall you would have a positive charge on that atom. And you would call it an ion, either a positively charged ion or a negatively charged ion. So if you gained electrons on an atom, that would give you a positively charged ion, which is also called a cation. If you lost electrons from an atom, that would give you a negatively charged, actually it's the other way around. If you gained electrons on an atom, that would give you a negatively charged ion, which you call an anion. If you lost electrons from an atom, that would give you a positively charged ion, which is called a cation. And this diagram is kind of showing an example of that for the sodium atom. On this side, you have the normal version of that atom. In the center here, where it has Na, the Na just symbolizes sodium, but that's also representing where the nucleus would be. And then around it, you have the electrons shown by these blue dots. So if you were to take one of these electrons away, that would give you less electrons on the atom, but you still have the same number of protons. So now you have more protons and electrons, which gives you a positive charge overall, which is symbolized by this plus sign. So this would be a positively charged ion or a cation. So if you start changing the number of electrons, you get an ion. If you start changing the number of neutrons, you get an isotope. An isotope is just an atom that has a different number of neutrons from the regular version, and it's going to have the same charge as the regular version, so no charge, because neutrons don't have a charge, but it will have a different mass than the regular version of the atom. So for instance, for carbon, normally it has 6 protons or 6 neutrons, 6 protons and 6 neutrons for 12 particles in the nucleus total, or a mass number of 12. So you could call that just kind of carbon. Sometimes it's also called carbon-12, and that's considered like the regular version of the carbon isotope. So you could actually use the word isotope to refer to any actually version of an atom, no matter what number of neutrons it has. But of course, the one that's most commonly occurring, where the number of neutrons is the same as the number of protons, that's the regular version, which is sometimes called an isotope and sometimes not. Then if you start adding neutrons to that, you're going to get something else, some other less common isotope. So if you added 1 neutron to a carbon atom, you would have 6 protons and 7 neutrons for a mass number of 13, and that would give you the carbon-13 isotope. If you added 2 neutrons, then you would have 6 protons and 8 neutrons. That would be the carbon-14 isotope. So in each of those isotopes, carbon-13 and carbon-14 has extra neutrons. It still has the same charge as the normal carbon atom or the carbon-12 isotope, but it does have more mass since it has more neutrons on it. And that's kind of shown in this diagram here. So over here you have regular carbon, or the carbon-12 isotope. You have 6 protons in the nucleus, and you also have 6 neutrons in the nucleus in blue. Then if you start adding neutrons, first if you add 1 neutron, you get the carbon-13 isotope. So you still have 6 orange protons in the nucleus, but now you have 7 blue neutrons. And then if you add 1 more neutron, you would have carbon-14, which has still 6 protons in the nucleus, but now 8 neutrons. So these all have the same charge, but carbon-13 is a little heavier than regular carbon or carbon-12, and carbon-14 is even a little heavier still. So the atomic mass is the mass of an atom. The atomic weight is the average mass in a sample of an element that's accounting for all the different isotopes that are there. So, of course, most of the atoms in any sample of an element will be kind of, the regular version of that atom or the regular isotope. So for carbon, it would be carbon-12. But isotopes are naturally occurring in kind of really small amounts. So anytime you have a pure sample of an element, you will have a little bit of those other isotopes. So if you have a pure sample of carbon, like maybe you have a diamond, that's pure carbon, most of those atoms in there will be carbon-12 or the regular kind of version of carbon, but you will have a few of them that are carbon-13 or carbon-14. So if you were to look at the overall average mass of all the carbon atoms in that diamond, it wouldn't just be the atomic mass of carbon, which is 12. It would be a little bit heavier because you have a few of those heavier isotopes in there. So the atomic weight is that average mass, and it's accounting for the isotopes at whatever small frequency they occur at, and so it's going to be a little bit bigger than the atomic mass. For carbon, the atomic mass is 12 daltons, and the atomic weight is 12.011 daltons once you've accounted for those heavier isotopes. So if you start changing the number of electrons on an atom, you get an ion. If you start changing the number of neutrons on an atom, you get an isotope. But if you were to change the number of protons on an atom, then you would just have an atom of a different element. You wouldn't have a special type of the atom for that element. You would have a different element entirely. So for carbon that has 6 protons, if you were to add a proton to it and have 7 protons, now you don't have carbon anymore. Now you have nitrogen, which is the element that has 7 protons. So I said that isotopes have a different mass than the regular version of that atom. Some isotopes also are unstable though, and they will decay and produce radiation. So those are considered unstable isotopes or radioactive isotopes. Depending on what type of radioactive isotope you have, that's going to determine what type of radioactive decay it undergoes. So there's different ways that these unstable isotopes can decay and different types of radiation that they can give off. An example of an unstable and radioactive isotope is carbon-14. So carbon-14 over time will spontaneously decay and emit radiation. What actually is happening there is that one of its extra neutrons is going to convert into a proton and release an energetic electron and a particle called an antineutrino. So you're left with, one less neutron in that carbon-14 isotope, so it's not carbon-14 anymore. Instead, you have an extra proton. So now you have not just 6 protons, but 7, which means that you don't have carbon at all anymore. Instead, you have nitrogen, because nitrogen is the element that has 7 protons in its atoms. So that carbon-14 has converted to nitrogen, and it's also lost or given off an electron and an antineutrino particle. The electron is actually the particle that is considered radioactive there, because it's very, very highly energized. The antineutrino doesn't really affect anything. It's a particle that doesn't really interact with other particles very much at all, so it doesn't really have any effect on anything. So this diagram here is showing the decay of the carbon-14 isotope. So one of these blue neutrons in the carbon-14 nucleus is going to convert into a proton, which means that now you have an extra proton there. So this is now nitrogen, and it's also at the same time going to give off an electron, which is radioactive. And it also gives off an antineutrino, but that's just not shown in this diagram. What is shown is that the electron is considered, radioactive because it's so energetic. This is called beta decay, but you don't need to know that. The kind of importance of this radioactive decay of unstable isotopes is that it lets you date samples of old things. So each one of these radioactive isotopes is going to have a half-life. The half-life is the amount of time that it takes for half of the isotopes in a sample to decay. So if you have, let's say, a diamond that's going to have some amount of carbon-14 in it, the half-life is how long it takes for half of all the carbon-14 isotopes in that diamond to decay to nitrogen-14. So if you know that half-life and you know how much carbon-14 you start off with, or you should start off with, then you can kind of figure out how much time has passed since that diamond, for instance, was created, if you're able to measure how much carbon-14 is left. So if you know how much was in the diamond when you first made the diamond, and you're able to measure how much is left now, and you know how long it takes for the isotope to decay, then you can figure out how long that diamond has been around for. So this is used to date old things like dinosaur bones or asteroids that have landed on Earth, or the oldest rocks on Earth. They can be dated using radioactive isotopes. This graph here is kind of showing an example of that. So the half-life for carbon-14 is 5,730 years. So that means that, if you have, let's say if you had 5 grams of carbon-14, that would be, quite a lot. But if you did have 5 grams of carbon-14 and you waited 5,730 years, then you would have 2.5 grams of carbon-14 and 2.5 grams of nitrogen. So half of it would have decayed in that time period. Then if you wait another 5,730 years, then another half of what you had left would decay. So if you start off with 100% of the carbon-14, which is, all of the carbon-14 that you start off with, and you wait that 5,730 years, now you're going to have 50% left. If you wait 5,730 years again, you're going to have 25% left. If you wait 5,730 years again, you're going to have 12.5% left, and so on and so forth. So if you measure how much you have left, you can figure out how long or how many half-lives have elapsed, and how long has it been since you had your full amount of carbon-14, and that will tell you when that object was created. So now we'll start talking about how it is that electrons orbit their nuclei in an atom. So I said that they kind of orbit not in a set path like what a planet follows around a star, but they kind of have like clouds or places where it's more likely to find them or less likely to find them. So those places where it's very likely to find them would be called orbitals, or that's like kind of the area around the nucleus where you might find an electron. That's called an orbital. Every orbital can hold 2 electrons in it. And there's different orbitals that have kind of different shapes, different amounts of energy that are associated with them, and different sizes, but we kind of categorize them based on their shape. And each shape has kind of a letter that describes it. So the simplest shape is just a circle, and that's the s orbital. Then you have the p orbital, then a d orbital, then an f orbital. You actually have more beyond that. You have like g orbitals and h orbitals, but we won't worry about them. So this kind of diagram is showing the shapes of those different orbitals. So here's the s orbital, just a ball around the nucleus. That's the simplest one. Then you have the p orbitals here. There's actually 3 different p orbitals. Each one can hold 2 different electrons in it. and they're kind of like almost like a what do I want to say? They're kind of like a smushed ball on either side of the nucleus. So you can have them on either side in the x-axis, x-axis, sorry guys, on either side going up and down, which here is labeled as the z-axis, or on either side from front to back, which here is labeled as the y-axis. Then you have the d orbitals, which you can see have even a more complicated shape, and there's 5 of them. Each of these can hold 2 different electrons. This one has a really weird shape. And then the f orbitals, there's even more of them. There's 7 of them. Each one of these can hold 2 different electrons, and they have really complicated shapes. So we don't need to worry, about what these shapes are exactly, but they're very complicated, as you can see. Sometimes you'll have different orbitals that have different shapes that have still like roughly the same amount of energy. So for instance, you can have an s orbital that has roughly the same amount of energy that a p orbital has. In that case, you're going to group those 2 orbitals together in what's called an electron shell. And then those different shells that you have are numbered. So the first one is 1, and then you have 2, 3, and 4. The bigger the number is, the bigger the shell is, which means the orbitals in that shell are kind of larger in size, and the more energy that they have. So if you're going to name any individual orbital, not only do you have to use the letter that represents its shape, but you also need to use the number that's representing its electron shell, which is like kind of its size and the amount of energy that it has. So the simplest orbital that you can have is actually 1s. That's the s orbital in the first electron shell. Then, beyond that shell, you have the second electron shell. So you can have a 2s orbital and a 2p orbital. Those are the s and p orbital in that second electron shell that have kind of roughly the same size or same amount of energy as each other. And so on from there. As you go up in shells, the kind of size gets bigger, the energy gets bigger, and the amount of orbitals in each shell also is going to go up. So this kind of study of like what these electron shells and what these orbitals look like, this is all quantum mechanics, which means that we don't really need to get into the details on it for sure. Also, something to bear in mind is that like no one knows what this stuff actually looks like. So all these diagrams here that have these really complicated shapes for these orbitals, we don't know if it looks like this exactly. This is kind of our kind of mathematical description of what we think it might look like, but no one knows for sure. So if we start looking at like specific electron shells and the orbitals that they have, we'll just stick to the smallest ones that are the simplest. So first we have, the first electron shell, number 1, and it just has an s orbital in it. So it's the lowest energy shell, it's the smallest shell, and only one orbital kind of has an amount of energy that is that low, and it is the first s orbital, like the smallest one. So 1s is the only orbital that you have in the first electron shell. It's just a ball. In this diagram here, it's represented by this gray circle. So at the very center here, you would have the nucleus of this atom, and then this gray circle around it is the 1s orbital, the simplest orbital in the simplest electron shell, the smallest orbital in the smallest electron shell with the least energy. And you're going to have 2 electrons that can fit in that orbital. Since you only have one orbital in the first electron shell, that means you only have 2 electrons that can fit in the first electron shell. Then after that, you have the second electron shell, which is bigger and has more energy. So you also have an s orbital in that one. You have the 2s orbital in the second electron shell. And you have p orbitals. You're going to have 3 different p orbitals. The ones that are pointing up and down, then kind of side to side, and then kind of front and back. Each of these, like front and back, side to side, and up and down, can hold 2 electrons. And you would call them the 2p orbitals because they belong to the second energy, or the second electron shell. So in the second electron shell, you have the 2s orbital, and then you have the 3 2p orbitals. Each of them can fit 2 different electrons in it, So that means you have 8 different electrons that can go into the second electron shell. So this kind of see-through reddish ball here, that is actually the 2s orbital. And then you have this one 2p orbital, another 2p orbital, and the third 2p orbital. Each with 2 electrons in it for 8 electrons total in that energy shell. After that, once you get into the third electron shell, it gets a bit more complicated. And we're not going to really worry about the details there. But the third electron shell is also able to hold 8 electrons. A lot of the time, if you're drawing atoms out, of course, you don't want to draw like all those orbitals. It gets like, that makes a really complicated drawing. So we kind of just symbolize it. So this drawing here is what we call a Bohr structure. You have the nucleus shown in the center, and then around it you have rings. Every ring represents an electron shell. So the first ring is for the first electron shell. That just has the 1 orbital in it, 1s, and so you only have 2 electrons that can fit there, and you can see they're drawn in. Then above that we have the second electron shell, which has 1 s orbital and 3 p orbitals. So that's the 2s orbital and 3 2p orbitals. So that's a total of 8 electrons that can fit there, and you have 8 electrons drawn in along that ring. And then above that you have the third electron shell, which also fits 8 electrons. And then if you had to add more shells, because this is like a bigger element, then you would put extra rings. The heavier the element is, the more that means like the more neutrons and protons it has in its nucleus. That also means it's going to have more electrons in it, and you're going to need more orbitals to kind of fit all those electrons. So you're always going to kind of put your electrons in the lowest energy orbital that you can put them in. So you fill up those, like the 1s orbital first, but then, if you have 3 electrons, only 2 will fit in the 1s orbital. So you're going to have to put that last electron in, the 2s orbital. You're going to have to, start putting them in bigger and bigger orbitals. So if you have a really heavy element with a large number of electrons in it, they're going to be, in kind of those really large orbitals in the bigger electron shells. So now we'll kind of turn back to the periodic table and look at kind of trends on the table as you're moving along the table. So if you kind of start on the left-hand side and you start moving to the right across a row, you're going to see that every time you move, the number of protons goes up by 1, the number of neutrons goes up by 1. So from lithium to beryllium, you're adding 1 proton and 1 neutron, also of course 1 electron. So as you're going across, those numbers start to go up, which means that the atomic mass is increasing. The mass of each of these elements is just a little bit bigger than the mass of the element previous. Also, as you go across, every time you're adding 1 electron, which means that you're starting to fill up your orbitals. So if you start actually at the very top with hydrogen, you have 1 electron there, so you put that in your 1s orbital. Then if you go to helium, now you have 2 electrons, so you put that second electron also in the 1s orbital because it holds 2. But now you have, that's full. So when you go to lithium, now you have an extra electron. You can't put it in the 1s orbital anymore. You have to put it in the 2s orbital. Then when you go to the beryllium, you're going to put that electron into the 2s orbital maybe. And then, so on and so forth, adding electrons to your orbitals as you go. If you were to start at the top of a column and move down, now instead of, well, I guess you're kind of just moving in bigger jumps. So you're still going to have your proton number going up and the neutron number going up. It's just going to be going up, by more than 1 each time. It's going to be kind of jumping higher and higher. So your atomic mass is going to be going up too, but it's just going to be kind of jumping higher and higher instead of increasing by a little bit each time. And also, I guess the most important thing here to note is that every time you move down 1 rung in this column, you're adding another electron shell. So as you go across, you fill the orbitals. As you go down, you add electron shells. So in this first row here, you have just your first electron shell. You only have 2 electrons that fit there, so you only have 2 elements in this first row. If you go down 1, now you're adding, now you have added a second electron shell. You can fit 8 different electrons in that shell, and that is the reason why you have 8 different elements in this second row. If you go down one again, now you've added your third electron shell. That also fits 8 different electrons, so you have 8 different elements in this row. And if you go down again, now you've added your fourth electron shell. That's a much bigger shell that has even more orbitals in it and fits even more electrons, so that's why you have more elements in that row, and so on and so forth. Every time you go down, you add 1 electron shell. As you're adding these electron shells, not only is the mass of the atom getting bigger, but the size is getting bigger too. So the mass is getting bigger mostly because you're adding more protons and neutrons to the nucleus, because those are the parts of the atom that are heavy. But it's the electrons that are really kind of taking up space there with their really big orbitals. So as you add extra electron shells, each atom gets really a lot bigger than the atom before. So as you're kind of going across the periodic table, adding electrons to orbitals and electron shells, you're always going to start with the lowest energy spot that you could add an electron and move on from there. So you're always going to kind of fill the lowest energy shell that you have available before you start adding to bigger and bigger electron shells. So if you're starting with hydrogen that has just the first electron shell, you only need to put 1 electron, so you put it there in the first shell. Then when you go to helium, now you have 2 electrons. The first shell will fit 2 electrons, so they both go there into the first shell. When you go to lithium, now you have 3 electrons. So you're going to put the first 2 in the lowest energy shell that you have available, which is the first one, and then you have an extra one that has to go into the second electron shell. Then when you go to beryllium, now you have 4 electrons. 2 of them will go into the first electron shell with the lowest energy. Then you have 2 that need to go into the second electron shell. So you're always filling the lower energy shells before you start adding electrons to the higher energy shells. So for any shell, that's going to get filled completely before you add electrons to the next shell. But for orbitals, it's actually not that way. If we're talking about orbitals that are within a single electron shell. So the only, I guess, the first time that kind of comes into play is with the second shell, where you have 4 different orbitals. You have the 2s orbital, and then you have 3 different 2p orbitals, all in that second electron shell. Each of those orbitals is going to get 1 electron in it before any orbital in the second shell gets another electron. So for lithium here, you fill up your first shell, then you have 1 more electron, you put that into the 2s orbital in that second shell. And then for beryllium, you fill up your first shell, then you put your electron into the 2s orbital in the second shell, and then the next electron that you have doesn't go into the 2s orbital, it's going to go into one of the 2p orbitals. So actually I think I misspoke on the previous slide. I think I said that both of them would go into 2s. But no, actually one of them will go into 2s, and the next one will go into 2p. Sorry about that, you guys. Then if you go, 1 element over to boron, now you have even 1 more electron, so you're going to put your 2 electrons in 1s, into that first energy shell, or electron shell. Then you put an electron into the 2s orbital, then 1 into a 2p orbital. Then your last electron will go into a different 2p orbital. In carbon, you have even 1 more electron, so that last one will go into the third 2p orbital. So at this point, once you're at carbon, you have your first shell completely full, and every orbital in the second shell has 1 electron in it. So that means when you go to nitrogen and you add even 1 more electron, now is the first time that all those orbitals in that second shell have at least 1 electron in them. So now you can start adding the second electron to some of those orbitals. So now the 2s orbital will get its second electron, and now it's full. Then if you add 1 more electron for oxygen, now you're going to fill a 2p orbital with its second electron, and so on and so forth until you get to neon, where all of those orbitals in the second energy shell or in the second electron shell are completely full with 2 electrons each. So shells will fill completely before you start adding to a new shell. Orbitals within a shell will get 1 each before any of them gets a second. That ends up being important because single electrons that are like kind of by themselves in an orbital are more reactive. It's actually more stable if you have two electrons together within an orbital, like a pair of electrons there. Whenever you have electron pairs in an orbital, that's pretty stable. They're not very reactive. If you have an electron just kind of chilling out by itself, all alone in an orbital, then it's easier for something to come and react with that electron. So carbon here has 4 different electrons that are just all by themselves in an orbital, which means all 4 of these electrons are reactive. Neon, on the other hand, doesn't have any electrons that are by themselves. All of its electrons are in pairs, which means that's not reactive at all. None of those electrons are going to be reactive because they're all in a pair. Whenever atoms are reacting with each other, it's always going to be the outermost electrons that can potentially be involved in that reaction. The innermost ones will not have anything to do with the reaction. So it's only the electrons in the outermost electron shell that have the opportunity to react at all. So we call that the valence shell. The outermost electron shell is always called the valence shell. And that just means that it's the outermost one where you can actually have reactions occurring. So any electrons that are in that outermost shell, in the valence shell, are called valence electrons. Those are the electrons that could be involved in a reaction with, another atom. But that probably wouldn't happen to them if they're in a pair. So for a neon, its valence shell is the second electron shell, and so the electrons in that shell are valence electrons, but because they're all in a pair, they're not really going to react. For carbon, its valence shell is also the second electron shell, and all of the electrons in that shell are valence electrons, and because they're just by themselves, they don't have a pair, that means that they're quite likely to react. So carbon is overall much more reactive than neon is. It has 4 different valence electrons that can react, and neon has, even though it has 8 valence electrons, they're all in pairs, so they don't really react. So if you were to, so that's valence shells and valence electrons, and we have even one more valence word, which is the valence of an atom itself. So the valence of an atom is how many unpaired electrons it has in its outermost shell. So how many unpaired valence electrons it has. So for neon, all of the valence electrons that it has are paired. That means it has no valence. The valence of neon is 0. For carbon, on the other hand, all of its valence electrons are single. They don't have a pair. They are unpaired valence electrons, which means that carbon's valence is 4. If you look at nitrogen, that has in its valence shell, it has 1 pair here, and then it has 3 unpaired valence electrons. So that means the valence of nitrogen is 3. For oxygen, it has 2 pairs in its valence shell, and it has 2 unpaired valence electrons. So its valence is 2. Basically, the more valence an atom has, the more reactive it is, and the more bonds it can form. So for every valence that carbon has, it can form 1 bond. Same thing for nitrogen or any other atom actually. Each of these electrons, each of these unpaired valence electrons can react with a different atom to form a bond. So carbon has 4 electrons that can form a bond. It has a valence of 4, and it has 4 different electrons that could form a bond, which means it could make 4 different bonds. For nitrogen, it has a valence of 3. It has 3 electrons that are unpaired in its outermost shell that could form a bond. It could make 3 different bonds. For oxygen, it has a valence of 2. It can make 2 different bonds. For hydrogen up here, it has 1 electron. That is its valence electron. And its valence shell is the first electron shell. It doesn't have a second one. So hydrogen's valence is 1. It has 1 unpaired valence electron. It can make 1 bond. So the more valence an atom has, the more reactive it is overall in general, and that also is determining how many bonds it can form. So whatever the valence is for that atom, that is the number of bonds that it can form. So this slide is kind of mostly going over what I just talked about actually, but So now we're going to start kind of getting into the concept of chemical bonds, and we'll end up talking about like different kinds of bonds that you can make between atoms. But a bond or a chemical bond is just a link between atoms that, holds them together, so they can't just go apart from each other. They're like attached to each other. There's different types of bonds that you can have, but all bonds are going to involve some amount of sharing of electrons between atoms. When you have atoms that are sharing their unpaired valence electrons with each other, that kind of lets them gain a pair for those electrons that didn't have a pair, which increases the stability. So if you look, let's see, at this diagram up here, this is actually methane. Methane is CH4, so that's 1 carbon and 4 hydrogens for methane. This is actually the simplest molecule that is considered an organic molecule. But in any case, what's shown here are the valence electrons. So this ring around each of these atoms is the valence shell, or the outermost electron shell, and you have the valence electrons drawn in. And they are kind of color-coded based on what element they belong to. So the red ones belong to hydrogen, and the blue ones belong to carbon. So we know that hydrogen has 1 valence electron, which is shown on each of these hydrogens. We know that carbon has 4 valence electrons, and so that's those 4 blue dots. They're all unpaired, so we have these 4 blue dots, each in their own orbital within that valence shell, the second electron shell. And we have carbon forming bonds with these hydrogens. So in these bonds, the valence electron shells are kind of coming together so that these valence electrons can be shared. So carbon just has a single unpaired electron right here, and hydrogen just has a single unpaired electron right here. But when they come together and make a bond, now these electrons get to kind of exist together in a pair. They get to kind of form a pair with each other. And that is what is holding this bond together, basically. The fact that these electrons are now in a pair together, which makes them quite stable, that is what is kind of keeping this hydrogen attached to this carbon. And the same for all of these other bonds. So the reason why these bonds are forming is so that these unpaired electrons can gain a partner and be part of a pair, which makes them very stable. That's kind of the same thing that's shown down here. This is a diagram showing the formation of water, which is H2O, so 1 oxygen and then 2 H's, or 2 hydrogens. This kind of drawing of oxygen is a little bit different, but you have the innermost shell here shown here with the 2 electrons in it, and then you have the outermost or valence electron shell for oxygen, which is the second shell. So oxygen is going to have 6 electrons in its second shell. So you would have like you would add them like 1 here, 1 here, 1 here, 1 here, then you would add 1 here and 1 here. So that would end up you having 2 pairs. So these pairs are just shown in a little bit of a weird fashion. They're not like shown real close together, but they actually are pairs. So this is 1 pair, and then this is 1 pair. And then here are oxygen's 2 unpaired valence electrons, which would be giving it its valence of 2. Then hydrogen, of course, has just its 1 electron, so has a valence of 1. When hydrogen is coming in to form a bond with this oxygen, it's going to end up sharing its electron with the unpaired electron that oxygen has here, so that those 2 electrons can kind of come together and make a pair. And the same thing happening up here with the other hydrogen. So now it's like hydrogen has a pair here in its valence shell. And then oxygen, it's like it has, it started with 2 pairs already, but it had 2 unpaired electrons, but now it's like each of those unpaired electrons is part of a pair. So now that's very stable. For oxygen, that's looking very stable. It's got all its electrons in pairs. For hydrogen, same thing, looking very stable. Its electrons are all part of a pair now. So that is basically what's holding that water together, the fact that electrons are stable when they're in pairs. Yeah, and just again to reiterate, however many unpaired electrons an atom has on its outermost electron shell, that's going to determine how many bonds it can form. Every one of those unpaired electrons in the outermost shell is able to make a bond and share with the electron from another atom to kind of form a pair. So now we'll talk about kind of the most common types of bonds that we're going to see in biology. There's actually more types of bonds than just this, but they're not really as important to us in biology. So first we have covalent bonds, then ionic bonds, and finally hydrogen bonds. A covalent bond involves electrons being kind of equally shared between two atoms that are a part of the bond. So they're actually like sharing their electrons with each other. Both of those atoms still has kind of some like grip or claim on its electrons. And then you have ionic bonds. In an ionic bond, electrons are actually transferred from one atom to the other atom, so they're not really being shared. It's just that one atom is going to steal the electron from the other atom. Whenever you have that happen and the electron is stolen, that means you've created two ions, and their charges are going to kind of hold them together. And then hydrogen bonds, we're going to talk a lot more about, but a hydrogen bond is kind of a weak interaction between a partially charged hydrogen on one molecule and a partially charged oxygen or nitrogen on another molecule. So tracking back to these covalent bonds, we're going to go over all these bonds in a little more detail, especially the hydrogen bond, but tracking back to the covalent bond for now, you have in a covalent bond two atoms being shared between, or two atoms sharing electrons between them. You have two different types of covalent bonds, or subtypes of covalent bonds. First, you have the nonpolar covalent bond, then you have the polar covalent bond. In a nonpolar covalent bond, the electrons are like perfectly in the middle of the bond. Each atom in the bond has an equal kind of claim on its electrons, and they're sharing them equally with each other. In the polar covalent bond, the electrons are being shared, but not equally. One atom is kind of hogging them to itself, so the electrons are going to be closer to that one atom and a bit further away from the other atom, even though they are still being shared. So some examples of that, of the nonpolar covalent bond, are right here, hydrogen and methane. So here you have, the nuclei of these atoms being represented by the letters, and then the line between them is representing the bond, and then you have the electrons drawn in on either side of the bond. So these are all nonpolar covalent bonds, which means that the electrons in the bond are perfectly in the middle of the bond. So you have your hydrogen atoms kind of gripping those electrons, and carbon is also gripping the electrons, and they're both gripping them with equal strength, so that the electrons end up in the middle, equally shared. Over here, with ammonia and water, you have some examples of polar covalent bonds. So in these types of bonds, the electrons are not going to be perfectly in the middle. They're going to be closer to one atom or another. And in this case, you can see that they're closer to the nitrogen in ammonia, and they're closer to the oxygen in water, and they're further away from the hydrogen. In both of those molecules, they're always going to be kind of further away from the hydrogen. The reason is the hydrogen tries to pull in those electrons, but it doesn't pull very hard. Nitrogen and oxygen pull real hard on electrons, so they're going to pull the electrons in close to themselves, and the hydrogen tries to pull them back, but it just can't do a good job. So it doesn't kind of lose its grip on them entirely. It's still sharing them with the nitrogen or with the oxygen, but it can't hold them close to itself. The electrons will end up near to the nitrogen or near to the oxygen. And then over here we have the ionic bonds, where electrons are being completely transferred from one atom to the other. So in this case, chlorine kind of grabbed the electron on this sodium so hard that it basically just ripped it off and took it for itself. So chlorine just stole that electron entirely. So what happens when sodium loses an electron is that it gets a positive charge. So now it's a positively charged ion. And when chlorine steals this electron and gets an extra electron, now it has a negative charge. So it's a negatively charged ion or an anion. And now you have a positive charge next to a negative charge, and they attract each other. So it's just the attraction between the charges that is holding this type of ionic bond together. So you have one atom steal an electron from the other. That means that now you have two different ions that have opposite charges, and their charges will attract, and that holds the bond together. Every time you have this type of ionic bond occurring, that's going to make a salt. So sodium chloride, that's like table salt. Anytime that you have, a positively charged ion bonded to a negatively charged ion as part of an ionic bond, that's always a salt. Then finally we have the hydrogen bonds. So in a hydrogen bond you have two different molecules interacting with each other. It's not just a single atom interacting with another single atom. It has to be two different molecules. And it has to be a hydrogen on one of those molecules with a partial positive charge on it, and an oxygen or a nitrogen on the other molecule with a partial negative charge on it. And then it's those partial charges that are attracting each other, more similar to the ionic bond. So if we look at water here, you can see this funky little symbol above the oxygen and another funky symbol next to the hydrogen. Those are partial charge symbols. So this is a partial negative charge on this oxygen, and this is a partial positive charge on this hydrogen. There's actually partial charges on them because of it being a polar covalent bond between the oxygen and the hydrogen in this molecule. So the oxygen is hogging the electrons all to itself. The electrons are real close to the oxygen. They're pretty far from the hydrogen. Since the electrons are real close to the oxygen, it's almost like the oxygen has extra electrons. It doesn't quite have extra electrons because it didn't completely steal them, but it has more of them than its kind of fair share, let's say. So it has a partial negative charge. The hydrogen hasn't lost electrons exactly, but it's almost lost the electrons. It's barely hanging onto them by a thread, and they're like pretty far away from the hydrogen. So that means that the hydrogen has almost lost electrons. It's almost like it's lost electrons, and that gives it a partial positive charge. So if you have a partial positive charge on this hydrogen, the same thing over here in ammonia. You have partial positive charges on these hydrogens and a partial negative charge on this nitrogen. So let's say you have a partial positive charge on this hydrogen in water. If this hydrogen comes near to this nitrogen with a partial negative charge, they're actually going to be attracted to each other because negatives and positives attract. So they're going to kind of have a tendency to stick near to each other just because they're attracted to each other by their partial charges. And that's the basis of the hydrogen bond. So the covalent bond is kind of the strongest type of bond out of all of those. Actually, the nonpolar covalent is like the actual strongest type, and then you have the polar covalent is a little weaker, ionic bonds are a little bit weaker, and then the hydrogen bonds are the weakest out of all of those types. Actually, if you are looking at like a chemistry textbook, it might tell you something different. It might tell you that ionic bonds are stronger than covalent bonds. It actually depends on the conditions that you're testing it in. But if you have water around, then ionic bonds are weaker. Water can kind of pull ionic bonds apart. So you know that if you put salts in water, it'll dissolve in the water. That's because the water is actually pulling apart those ionic bonds. So if if you're looking at things that are in water, then covalent bonds are stronger than ionic bonds. And when we're talking about biology, we're always talking about something that's in water because organisms are mostly, they're mostly water. Then once you've got like bonds formed between atoms, that creates a molecule or a compound. So if we want to get technical, like the kind of chemistry definition of those things is that a molecule is multiple atoms bonded together and they're not charged. A compound is multiple atoms bonded together and they could be charged or they might not be charged. So technically there's a difference between those two words. But in biology, that doesn't really matter to us. So we just treat them like they're the same thing. So, if you hear me say molecule or compound, like it just means the same thing. It means, multiple atoms bonded together, whether charged or not. If it's your chemistry class, they might want you to know that distinction. But in biology, it doesn't matter. So sometimes you might not have just one covalent bond between two atoms, but you might have, 2 or even 3. So if you have, I guess I should say for every covalent bond between two atoms, that represents one pair of electrons that is being shared between those two atoms. One atom brings one electron, the other atom brings a second electron, they come together and make a pair, and that's a shared electron pair that is forming that covalent bond. So if you had not just the one electron pair that's shared in the bond, but actually two different electron pairs that are being shared, that would mean you actually have two different covalent bonds between those two atoms, and we call that a double covalent bond. Then if you added even a third pair of shared electrons, that would be a third covalent bond, and we call that a triple covalent bond. So those types of bonds can form between atoms, but they can only form if each atom that's participating in the bond has at least that number of unpaired valence electrons. So hydrogen, for instance, just has one unpaired valence electron, so it can only form a single covalent bond. It can't form a double. Oxygen, on the other hand, has two unpaired valence electrons, so that means it could form a double bond, but it can't form a triple covalent bond. So here you have that kind of shown in this type of notation that each bond is shown by just a line. So in a single bond or a single covalent bond, you have, just a line between the two atoms. If you have a double covalent bond, then we put that as 2 lines. If it's a triple bond, we put it as 3 lines. Or in these diagrams that are kind of showing actual electron pairs that are shared, at the top you have the single bonds that we already kind of have been talking about, and on the bottom you have double bonds or triple bonds. So in the double bonds here for carbon dioxide, each of these oxygens has 2 different bonds it's forming with the carbon, and you have 2 electron pairs represented. So these 2 are part of one covalent bond, and then these 2 are part of the second covalent bond. Nitrogen has 3 unpaired valence electrons, so it can actually form triple bonds. And so here you have nitrogen forming, 3 covalent bonds with another atom of nitrogen, and you have 3 different electron pairs that are shown here representing that triple bond. So we'll talk just a little bit about how molecules are shaped, because it can affect how they behave chemically. In anatomy, we have the phrase form follows function, but actually it should be the other way around. Function follows form. Basically, it just means that the way something is shaped determines how it can behave. So the way the structures of your body are shaped determines the functions that they can have or the purposes they can serve in the body. And it's kind of the same thing for molecules, or I should say, yeah, for molecules. The way that they're shaped kind of determines something about what types of reactions they can undergo, or how they could function in the body. So the way that a molecule is shaped is determined by the way that its bonds are shaped. The way that bonds are shaped has just a few different things that influence it. So first, electrons don't like to be next to each other, so they will repel each other because they have negative charges, and negative charges don't like to be next to each other. So when you have 2 electrons that are kind of together in an orbital forming a pair, those electrons actually are fine being next to each other. They don't mind it. They actually like to be next to each other in that case. But apart from that, they don't like to be next to each other. So if you have, one electron pair in one orbital and then another electron pair in a different orbital, they don't like to be close. They will try to push each other away and be as far away from each other as they can be. So part of the shape of the molecule is determined by just those electrons trying to get away from each other. Then you also have the bond type influencing things. If you have a single covalent bond, then the atoms that are participating in that bond can rotate freely, which could affect the shape of the rest of the molecule. If you have a double covalent bond or a triple covalent bond, then you can't have that rotation. They have to be linear. They can only, be in a certain shape. A certain spatial relationship to each other. So if you're talking about a molecule that only has single bonds, you have free rotation at all of the bonds. All of the electrons will be kind of determining the shape of that molecule. They'll just be pushing each other away from each other, they'll be pushing away from each other, which means that all of the bonds will be as far away from each other as they can be. If you have a molecule that has double or triple bonds, then some electrons might have to be, a little closer to each other, and the molecule will be forced to be linear or straight in some portions of it. So you have some examples of molecule shape here in these diagrams. First, you have methane and water. Methane is a carbon atom with 4 hydrogens attached to it. That is forming a tetrahedron shape, which is kind of a classical shape to be formed anytime that you have a central atom with 4 other atoms attached to it, and it's all with single bonds. So in the tetrahedron, it's kind of shaped like a pyramid, basically. You have 5 different atoms there always, and 4 different single bonds. The carbon's always in the middle, and then you're going to have the hydrogens attached to it. And basically the electrons that are shared in those bonds are just going to be trying to get as far away from each other as possible, so they'll be pushing each other away, and this is the shape that they form when they are all as far away from each other as they can possibly get. In water, you have almost a similar thing happening in a way. You only have, of course, 3 atoms in that molecule, so you have your central oxygen and then 2 hydrogens attached to it. So they're trying to be as far away from each other as possible. So you might think that it would just be straight. The hydrogens would just be on either end of the oxygen, but they're actually just kind of both off to the same side. And the reason is that you have the other electrons on oxygen also trying to get away from the electrons that are in the bond. So oxygen has, 2 pairs of electrons in its valence shell, and then it has its single electrons that it got to be pairs by sharing them with hydrogen electrons as part of a bond. So these electrons, both the paired ones that oxygen has and the ones that are part of a bond, are all trying to get away from each other, and that's why you end up with the 2 hydrogens kind of pushed off to the same side. So if you were drawing in those other electron pairs that oxygen has, then it almost kind of looks like that tetrahedron shape. It's pretty similar. Since there's no atoms attached there, the actual molecule is just shaped like a triangle, but it's because of those other electrons pushing the hydrogens to the side. Then down here we have some molecules that have double bonds in them. So here you have carbon dioxide with double bonds between the oxygens and the carbon. So those things are always just trying to be as far away from each other as they can, but also you can't have any rotation here between the oxygen and the carbon. They have to be straight, or else this bond would actually kind of break. So the bond is holding it straight. It has to be just a straight line like this, irregardless of what other electron pairs oxygen might have or anything like that. And then here, with nitrogen dioxide, you have nitrogen with one oxygen attached to it using a double bond, and another oxygen that's attached to it just with a single bond. And then you also have an unpaired, or no, you have a pair. You have a pair of electrons over here on the nitrogen, which is represented by this tiny blue dot. So these electrons are not participating in any bond. They're just the paired electrons that nitrogen has in its outermost shell. And they're actually going to end up influencing the shape of this molecule. The shape is just a little bit bent. So this bond between the nitrogen and the oxygen that has a double bond, that has to be straight like that. It can't be another way. But this bond is a single bond, so this bond can rotate and move around. So these electrons, these paired electrons here, are going to be kind of pushing the electrons in this bond away, and they're just going to be kind of trying to get as far away from each other as they can, and also as far away from this guy as they can, and then this guy with the double bond, he can't move. So that's why you end up with this just bent shape. So there's another feature or characteristic that atoms of different elements have that we haven't talked about yet that ends up being really important for biology, which is electronegativity. Electronegativity is just how strongly an atom is able to attract electrons in towards its nucleus. There's 2 main factors that determine how much electronegativity an atom will have. First, the amount of protons in the nucleus, and second, the number of electron shells around the nucleus. So a very electronegative atom is going to attract electrons in towards its nucleus really strongly. The way it would do that is by having a lot of protons in its nucleus. More protons in the nucleus means more positive charge in the nucleus, and since positive charges attract negative, that means the electrons will be pulled in more strongly towards the nucleus. The electron shells around the nucleus, though, are going to kind of block some of the pull that protons have on the electrons in the kind of outermost electron shells. So if you're an atom of an element that has a lot of electron shells around it, your outermost electrons, which are the ones that we most care about, since those are the ones that you're reacting with, those outermost electrons will be kind of pretty distant from the nucleus, and you're going to have a lot of other electrons in between those outermost electrons and the nucleus. So even though you might also have a lot of protons pulling really strongly, that pull is going to be blocked by all the intervening layers of electrons between you and the nucleus. So that is kind of shown in this diagram here. Over here you have oxygen, which has 2 electron shells, and on the right side you have sulfur, which has 3 electron shells. So if you're an electron in the outermost shell in oxygen, you only have 1 layer of electrons in between you and the nucleus. So that layer of electrons, which only has 2 electrons in it, is going to be kind of blocking the pull of protons in the nucleus on you. But since there's only those 2 of them, it's not a very strong kind of blockage. They don't block strongly. If you were an electron in the outermost electron shell of sulfur, on the other hand, not only do you have those 2 electrons in the innermost electron shell, you also have the second electron shell full with 8 electrons, and all of those electrons are going to be blocking the amount of pull that you experience from the protons in the nucleus. So you're going to experience a lot less pull. Even though sulfur has a lot more protons than oxygen has, it also has that extra full electron shell, which is going to block the pull. So here on the periodic table, you can see the electronegativities of different elements. Red is kind of high, yellow is like moderate, while yellow and kind of green is like moderate low, and then blue is low. So the elements that we care about most would be kind of hydrogen, carbon, nitrogen, and oxygen. So you can see that carbon and hydrogen are both kind of medium in the amount of electronegativity that they have, and nitrogen and oxygen are really high. For oxygen, it has kind of a lot of protons, but it only has that 1 electron shell in between, the outermost electrons and the center, or the protons in the nucleus. That's what makes oxygen so electronegative. The fact it has a lot of protons compared to not a lot of electrons blocking the pull. Electronegativity ends up being really important for determining what type of bond 2 atoms will form if they form a bond. So if you have 2 atoms of different elements that have a really large electronegativity difference between them, they're actually going to make an ionic bond. An example of that would be sodium over here, which is low on electronegativity. If that bonds with chloride, which is high on electronegativity, that's a really big difference. From high electronegativity to low electronegativity with sodium. So that's actually such a big difference in electronegativity. The chloride is going to pull on those electrons so hard that it's actually going to pull an electron right off of the sodium. Sodium tries to pull in its electrons, but it just can't really do it very well at all. So whenever sodium bonds to chloride, the chloride will actually steal an electron, and that creates an ionic bond. So it's that extreme electronegativity difference between sodium and chloride that actually causes those 2 atoms to form an ionic bond when they bond together. On the other hand, if you have like a more moderate difference in the electronegativity of the 2 atoms, but it's still it's significant, but it's not like huge, then you're going to get a polar covalent bond. So an example of that would be like oxygen binding to hydrogen to make water. So hydrogen is moderate in electronegativity and oxygen is high. So, with chloride bonding to sodium, that's like high versus low. With oxygen binding to hydrogen, that's high versus medium. So that's going to be a more moderate difference in the electronegativity that makes a polar covalent bond, where once they're in the bond together, oxygen is pulling really hard on the electrons, hydrogen is only pulling kind of hard. Oxygen doesn't pull hard enough overall to steal electrons from hydrogen, but it does pull hard enough to kind of hog them to itself and keep those electrons over towards the oxygen side of the bond, which gives you the polar covalent bond. Then finally, if you have like no difference in the electronegativity of the two atoms or only a small difference, then you're going to get a nonpolar covalent bond. So for instance, if you have carbon binding to hydrogen to make methane, those are both moderate or medium on their electronegativities. So they're not literally equal, but they're pretty close. So they both pull about equally hard on the electrons, and they're going to end up sharing those electrons equally in the bond, giving you the nonpolar covalent bond. So let's see, before we move on from this slide, I just want to mention or point out that oxygen is actually the second highest element in terms of its electronegativity out of all the elements. Only fluoride is more electronegative than oxygen is. But of course, fluoride isn't really common in organic molecules or in organisms. Oxygen is very common in organisms. So oxygen being really electronegative is going to end up being important for the chemistry of organisms. So we had just mentioned that if you have two atoms come together to make a bond and they have kind of a moderate difference in their electronegativities, they're going to form a polar covalent bond where they are sharing the electrons, but one of the atoms is pulling on the electrons more strongly. Those electrons are going to be over towards, that atom that is pulling more strongly. Anytime you have that type of bond, you might end up with a polar molecule that has partial charges. So a good example of that is water. So you have oxygen, really high in electronegativity, bonded to hydrogen, which is medium on electronegativity. So the oxygen is going to pull those electrons in towards itself. The electrons will be kind of more over towards the oxygen side of the bond. And I guess I kind of already mentioned this already, but when the oxygen has those electrons over on its side of the bond, it's almost like the oxygen has extra electrons. The hydrogen, on the other hand, is almost missing electrons since they're so far away from it. And that's going to give you partial charges on those atoms. So oxygen that almost has extra electrons is going to get the partial negative charge. Hydrogen that is almost missing electrons will get a partial positive charge. And we always represent partial charges using this kind of funny looking D, which is actually the lowercase Greek delta letter. And then we have a plus or a minus to indicate if the charge is, partial positive or partial negative. So the funny little d means that it's a partial charge, and then the plus or minus means, positive or negative. So anytime you have a polar covalent bond, one of these atoms is going to be partially negative, and one will be partially positive. Whoever is more electronegative will be partially, negative. Whoever is less electronegative will be partially positive. Then if you end up having kind of an overall asymmetry in terms of the charge distribution across the molecule, you're going to end up with a polar molecule. So basically, since in water you have both of these hydrogens off to the same side of the oxygen, that means you have two partial positive charges on the same side of the molecule. On the other side of the molecule, you just have oxygen, which has a partial negative charge. Technically, it actually has two partial negative charges because it's participating in two polar covalent bonds. That means you have kind of a positive side or a partially positive side of this molecule and a partially negative side of this molecule. That makes the whole molecule polar. If the shape of the molecule was different, then it would be different. So for instance, in water, if you had this hydrogen just over here, so that it was kind of linear, just a hydrogen in line with an oxygen in line with a hydrogen, just forming a line, that would actually not be a polar molecule, even though it has polar covalent bonds, because you would have just symmetry in terms of the charge distribution. You would have partial positive on both ends, not partial positive on one end and partial negative on the other end. So it's that asymmetry that you need to have actually a polar molecule. And over here is just a different way of showing that with water, that you have the electrons in those polar covalent bonds close in towards the oxygen, which gives it a partial negative charge, and the hydrogens have kind of lost their electrons in a way, almost, which gives them the partial positive charge. Since both those hydrogens are on the same side of the molecule, you end up with a partially positive side and a partially negative side, which makes it a polar molecule overall. The fact that water is polar like that ends up being really important for biology. That causes water to have a lot of special properties that are really important for life. And, there's a lot of polar molecules in biology, but by far and away, the most important one that we're going to be talking about a lot is water. Whenever you have two molecules interacting with each other, or reacting with each other, we call that a chemical reaction. There's kind of three different outcomes that you could have. Either you could be taking two molecules and kind of sticking them together to get something bigger and more complicated, or you could be taking one molecule and breaking it apart to get multiple simpler molecules. Or you could have two molecules come together and just kind of trade pieces with each other, and just exchange atoms between each other to form a couple of new substances on the other side of the reaction. When we write a chemical reaction out, we always do it in a standardized way so that on the left-hand side we have the reactants, which are the chemicals or molecules that we start out with, and on the right-hand side we have the products, which are the molecules that we end up with after the reaction occurs. So on the left-hand side you have the reactants, the molecules that will be reacting together. On the right-hand side you have the products, or the molecules that they create. Between the reactants and the products you have an arrow showing that the reaction goes from the reactants to the products, but actually sometimes it's a double-headed arrow, so it has the pointy end on both ends, and that just means that the reaction could go forwards from the reactants to the products, or once you have the products it could also go backwards and the products could form the reactants again. So there's actually a lot of reactions that could go both ways. Just kind of depending on what the conditions are, that'll determine whether it wants to go forward or whether it wants to go backwards. Whenever we're writing out a chemical reaction, we also have to make sure that we have balanced it, which means that the number of atoms on one side of the arrow has to be the same as the number of atoms on the other side of the arrow for each element. If we end up having a disparity, like maybe two oxygens on one side but only one oxygen on the other side, then we need to add some coefficients to show that we have multiple molecules of a particular substance so that it will be balanced. So for instance, in this reaction here, you have the reactants over on the left side, methane and oxygen. This is O2, so that's actually molecular oxygen, two oxygens bonded together to make a molecule, even though it's just oxygen. So those are the reactants. Then you have the arrow showing that they will react to form the products, which are water and carbon dioxide. So if we're going to make sure that this kind of equation is balanced, we would just kind of count how many atoms of each element we have on each side. So first we could start with carbon here. There's one carbon on the left, one carbon on the right. That's good. Then we have H, or hydrogen. There's 4 H's on the left because there's 4 hydrogens in methane. And on the right hand side we have water. There's 2 H's in water, so that gives us 2. That means we need to add a 2 as a coefficient in front of the water, so we would have 2 times 2 H's, which is 4 H's. So that gives us 4 on each side, so H is good. Then the last element that we have is oxygen. We have 4 oxygens shown here on the left-hand side. So in every molecule of molecular oxygen, you have 2 different oxygens, and then we're going to use 2 of them to make sure that this is balanced. So that's 4 oxygens total on the reactant side. Then on the product side, we have 1 oxygen in water, but we have two waters, so that gives us 2 oxygens there. And then in carbon dioxide, there's 2 more oxygens. So that's 4 oxygens on both sides. So that's balanced. Usually when you're seeing an equation in here, it will be balanced. In chemistry, you might have to actually balance equations, but in here we just, we show them balanced already. And then I guess the final point to make is that for any reaction that is able to go both ways, so it would have a double-headed arrow on it, eventually that reaction will reach something called chemical equilibrium, which is the state in which it's going forwards at the same rate as it's going backwards. So the reactants are reacting to make the products, and the products are reacting to make the reactants at the exact same rate, which means that overall you don't have any change in the number or the amount of reactant or product that you have. And because those amounts of reactants and products aren't changing, that's why we say that it's at equilibrium. So anytime that we're talking about chemical reactions occurring, we're going to have energy involved there, which we'll end up talking more about that a little bit later when we talk about like proteins and enzymes. But here we'll just go over kind of the basic types of energy that you have. So first off, energy itself. Energy is defined as the ability to do work or supply heat. And by work, we don't mean like, the work you do at your job necessarily. We mean like the physics definitions of work, which is like force applied to an object that causes that object to move. So it's force over a distance. That's like the physics definition of work. So the ability to make that happen, to apply force and make something move, that is the ability to do work, or creating heat. Those are the two things that that are energy. And then we have a bunch of different types of energy. This is only, some of them, is not even all of them. But first you have potential energy, which is just stored energy. So for instance, if you have a book on a table, we say that it has potential energy because if you move the table, then it's going to fall. Also, a battery has potential energy. It's storing energy. Then you have chemical energy, which is the capacity of a molecule to make stronger bonds than what it already has. So that's actually a type of potential energy that is it's the potential of a molecule to make stronger bonds than the bonds that are already making it up. So in general, a molecule that has a lot of chemical energy probably has a higher likelihood to react, since its bonds aren't that strong. It can make stronger ones, but also that's going to be really useful to organisms as a source of energy. Anytime you have a lot of chemical energy in a molecule, that means that you could react it to get it to make stronger bonds than the ones it has now, and when that happens, you're going to be releasing some energy from it, and you could, snatch that energy up and use it to get some work done. Actually, later on when we talk about carbohydrates, we'll talk about bond strength, but for now we'll just mention that a strong bond usually means that the electrons in the bond are closer to the nuclei. So if you have a bond where the electrons are very far from the nuclei of the two atoms making up the bond, which would be a longer bond, that's generally a weaker bond. If the electrons are really close to the nuclei of those two atoms, which would make a shorter bond, then it's a stronger bond. Then you have kinetic energy. Kinetic energy is not a form of potential energy. That is just the energy that's associated with any object in motion. So that includes, objects like ones that you can pick up and move, like ones that you could touch, but it also includes atoms. So when atoms are moving, they have kinetic energy associated with them. And then related to that, we have thermal energy, which is kind of like heat energy, but thermal energy is just, kinetic energy when it belongs to a molecule. So when molecules are moving, they have a type of kinetic energy called thermal energy. If you're able to measure the thermal energy of all the molecules in a substance, that is the temperature of that substance. And any time that thermal energy is being transferred from one substance to another, that's called heat. So that means that in a way, heat is just, that's kind of just like one atom hitting another and transferring its motion to that other atom. And then temperature is just kind of the average motion of all the atoms in a substance. So the hotter something is, or the more temperature it has, then the faster its molecules will be moving. When we have a chemical reaction occurring, that always means that energy is going to be transferred in one way or another between the reactants of the reaction and potentially between their environment as well. So generally, chemical reactions can be classed as either endothermic or exothermic. If it's an endothermic reaction, that means that it is going to be taking energy out of the environment. So that generally means that, like, in order to make that reaction happen, you have to put in some extra energy. Like, those reactants need to pick up some energy from the environment before they can react. So, thereby absorbing that energy. Endothermic reactions are useful, sometimes. So you probably might have encountered them in cold packs. Cold packs work by, just having an endothermic reaction going on inside of them that is sucking energy out of the environment, and that's why it feels cold. So if you touch it, it's actually kind of sucking energy out of you, and that's why it feels cold. And then that energy goes to fuel the reaction. Then you have exothermic reactions, where the reactants, when they react, actually are releasing energy out to the environment. So they kind of have, like, they're going to have more energy than what the products will have, which means that when they react to form the products, that extra energy ends up going out into the environment as heat or as thermal energy. So those are pretty common. Of course, fire is an exothermic reaction. That's the one we're probably all most familiar with. Also, warm packs, though, those work using an exothermic reaction that releases energy, to your hands to warm you up. And then this diagram is just kind of showing the basic difference between potential energy and kinetic energy in terms of a balloon. When the balloon is full of air, it has potential energy because all of this air could just come out of the balloon. So you have a lot of energy stored in this air inside the balloon. If you kind of release the balloon, then the air actually will come out, which means at that point you have air moving, so that is kinetic energy. So at that point, all the potential energy that the blown up balloon has will convert into kinetic energy as the air rushes out and the balloon deflates. And so now we get to touch on some physics real briefly, although I guess we kind of already did by talking about energy, but just a little bit more on physics. The laws of thermodynamics. The first law of thermodynamics is the law of conservation of energy, which states that energy cannot be created or destroyed, it can only change form. So whenever you have a chemical reaction, you're never going to make energy there. You might release energy or transfer it from one form into another, or from one place to another place, but you're never going to make it, or destroy it. Then the second law of thermodynamics states that entropy always increases over time. Entropy is kind of hard to describe, but it's basically how much disorder something has. So how unorganized something is how much entropy it has. The more unorganized it is, the more entropy it has. So if you have an extremely well-ordered desk or a well-organized desk, that desk has not very much entropy. If time passes and the mess accumulates on that desk, it is also accumulating entropy. So over time in the universe, entropy will always increase overall. You might have pockets that are ordered, but as time passes, entropy will always be going up overall. Entropy ends up being important, for a number of things, but for one thing, it's important in kind of determining if a reaction will just kind of go by itself, or if it needs something extra to be put into it before it can proceed. So a spontaneous reaction is a chemical reaction that will occur just on its own without any extra energy needing to be put into it. So that means the reactants don't need extra energy to react. They'll just go ahead and do it. In general, that means that those reactants are going to have more chemical energy than the products have. So they'll have more potential energy, but when a molecule has potential energy, we call that chemical energy. So for a spontaneous reaction, the reactants have more chemical energy, the products will have less. So you don't need to put in extra energy. You're actually going to release energy from that reaction. So it's going to be an exothermic reaction that releases energy in some way or other. And also in general, for a spontaneous reaction, the reactants are going to have less entropy and the products are going to have more entropy, since entropy always tends to increase. And this is a reaction that's just kind of happening by itself. So that means that usually the reactants are going to be kind of bigger or more complicated than the products, which would be smaller or more simple molecules. So they're less organized, which generally just means like simpler. So spontaneous reactions happen on their own, and usually that means that you have something complicated turning into something simple and releasing energy at the same time. However, in chemical evolution, we needed to have the opposite thing happen. We needed to have non-spontaneous reactions where you started with simple molecules and you put them together to get more complicated molecules. So that's not going to happen like just by itself. It needs extra energy to drive it. So we don't know exactly where that energy would have come from, but we think probably it came from lightning. So probably you had some of these simple molecules in the oceans that kind of evaporated into the air, went up into the clouds, and then you have lightning in the clouds, and that could have provided an energy source to drive some of these non-spontaneous reactions. Then you would have gotten some products that were more complicated than the reactants, and they could have fallen back to the oceans in rain. And the cycle could have repeated, and you're just forming more and more complicated molecules as you go along. Some reactants that we're probably used to hearing about a lot are acids and bases. So acids and bases are molecules that can change the amount of protons that you have in water. If you have a sample of water that's just like pure water, actually some of that water is going to react with itself. Some of those water molecules will actually spontaneously break down to give you hydroxide ions and hydrogen ions. So that's shown by this reaction here. So you have a water molecule breaking down to make a hydrogen ion right here, the H+, and the OH- is the hydroxide ion. And you see this is a double-headed arrow, so this reaction goes both ways. So if you're just waiting over time, some of these hydrogen ions will combine with hydroxide ions to make water. Some of the waters will break down to make hydrogen ions and hydroxides. This hydrogen ion, that's a proton. So hydrogen only has a proton and an electron. It doesn't have a neutron. If you're going to make a positively charged ion out of a hydrogen atom, you would need to take electrons away from it so you have more protons and electrons. But there's only one electron there in hydrogen, so once you've taken it away, there's none left. That gives you just a proton left over. So H+ is always just a proton. Actually, a lot of the time we will abbreviate protons using just H+. So anytime you see H+, that just means proton. And protons are important because they're really reactive, being just a single charged particle. Yeah, they're very reactive. So that ends up having a major effect on any organic molecules that are in the water. How many protons there are will affect those molecules in a big way. An acid could be defined as any substance that will lose protons in water. So it'll give up protons, which means that the water gets more protons. So the number of free protons you have in the water is going to go up if you add an acid to the water. A base could be defined as any substance that will gain a proton in water or pick up a proton from the water, which means that the number of protons you have just floating around in the water is going to go down if you add a base to the water. So that's kind of a really simple way of defining acids and bases. Actually, in chemistry, they have several different ways of defining acids and bases that tend to be a little more complicated than that. But for us, just an acid loses a proton and a base gains a proton in water. That's good enough. An acid-base reaction is a special type of chemical reaction where you have a proton moving from one molecule to another molecule. So for instance, if you put hydrochloride or hydrochloric acid into water, you're going to have it pulled apart and you're going to end up with just a free proton and the chloride ion. So that's an acid-base reaction because you start with a proton in hydrogen chloride and you end with just a free proton. So the proton is moving from hydrogen chloride to itself, I suppose, to being a free proton. And Another example is down here. You have sodium hydroxide here. If you put that into water, it's actually going to pick up protons from the water. So it'll combine with free protons in the water. Well, you know, for every molecule of sodium hydroxide, it'll combine with one free proton in the water to form just a sodium ion and a water molecule. So actually what's happening here is this proton is kind of kicking the sodium off, and it's combining with the OH to make a water. So that's also counting as an acid-base reaction. You're starting out with a proton that's a free proton, and it's being transferred to a water. We measure the amount of free protons that you have in a water-based solution using the pH scale. pH just means power of hydrogen. Since hydrogen ions are protons, that's why we call it that. The pH scale is not like a normal scale. It's actually a logarithmic scale, which means that every time you go up or down on the pH scale by 1 unit, you're not changing the amount of protons by 1, you're actually changing it by a factor of 10. So if you're starting at neutral and you go up 1, that means you're going up to 10 times more protons. If you start at neutral and you go down 1, that means you're going down by a factor of 10. So you would have 10 times less protons. The kind of formula that's used to calculate the pH of a substance is just pH equals the negative log of the hydrogen ion concentration. So these brackets here with the hydrogen ion in there, that means hydrogen ion concentration or proton concentration. So that's a negative log of the proton concentration. The fact that it's a log means that every time, you know, as I just mentioned, every time you're changing by 1 unit, that's actually a factor of 10 change. And then the fact that it's a negative log means that when you go up on the scale, you're actually having less protons. When you go down on the scale, that's when you have more protons. So if you were to calculate the concentration of free protons in pure water, so the amount of kind of water molecules that are spontaneously dissociating to make just free protons, you're going to end up with 0.0000001 protons in every liter of pure water. If you plug that into the formula, that gives you a pH of 7. So we define that as neutral. Anything that is pH 7 is a neutral pH, just the amount of protons that you would have in absolutely pure water. If you start adding acids and bases to the water, then the pH is going to start changing. If you added an acid to the water, it's going to lose protons in the water, which means the amount of protons or the concentration of protons in the water will go up, which means the pH will go down because it's a negative log scale. On the other hand, if you added a base to the water, it's going to kind of take up protons from the water, and the amount of protons you have in the water floating around will go down, which means the pH is going to go up. So anytime you have pH below 7, that means you're acidic. There's some acids in the water, and it is an acidic solution. Anytime the pH is above 7, we call that alkaline or basic. So there's less protons than what you would have in pure water, and there's some bases in the water that have taken up those protons. So pH ends up being really important to organisms because it's going to affect their molecules, in particular their proteins, which are the molecules that are doing most of the work that goes on in the cell. So proteins are actually acids and bases, which we'll get into when we talk about protein structure, but every protein both has the ability to lose protons as an acid or to pick up protons as a base. Which one it does, if it does either, is going to depend on the pH of the cell that it's in. So it's really important that the cell have the right pH that the protein is kind of designed to function at, so that it doesn't pick up or lose protons that it wasn't supposed to pick up or lose. It needs to have the right amount of protons in order to function properly. So if the pH changes and the protein either gains or loses protons, it might stop functioning at some point. So for that reason, organisms have to be sure that they're maintaining the right pH. So different organisms are adapted to live at different pH values. Most organisms live at a neutral pH like us, but you also have some that are adapted to live in a very acidic environment or a very basic environment. Whatever the environment they're adapted to is like, they have to be able to keep their pH like in that range, or else their proteins will stop working. In order to maintain a stable pH, organisms will use buffer systems. A buffer is any compound that is able to prevent the pH from changing when you add an acid or a base to the solution. So normally, if you added an acid to a water-based solution, it's going to lose protons and you end up with more protons in the solution, which lowers the pH. If you had a buffer there, though, then you wouldn't see that happen. The pH would maybe go down a tiny little bit, but not very much. On the other hand, if you add a base to a solution, to a water-based solution, normally it's going to pick up protons from that solution. So the amount of protons that are in the solution would go down, and the pH would go up. But if you have a buffer in there, that's not going to happen, and the pH might go up like a tiny bit, but not very much. So with a buffer, you can prevent the pH from going up or down when you add an acid or a base. All animals use a carbonic acid buffer system, which is actually sometimes called the bicarbonate buffer system. Carbonic acid is H2CO3, and bicarbonate is HCO3-. So if you have carbonic acid and you put that into water, it's actually going to dissociate and it'll lose a proton basically and form bicarbonate and the free proton. So that's what's shown in this equation here. You have carbonic acid, the H2CO3, dissociating in water to form bicarbonate, HCO3-, and just a free proton. This is a double-headed arrow, so this reaction can go both ways. So sometimes you could have this bicarbonate combining with the free proton to go back to carbonic acid. This diagram here is kind of showing how the buffer works if you were to add an acid to the solution. So you're starting off with a water-based solution here in this beaker, and you also have the carbonic acid buffer system in there. So you have some you have some carbonic acids, these H2CO3s right here. The blue part is the kind of bicarbonate part, and then the black part is the proton. So some of these will dissociate and leave just the bicarbonate, the HCO3-, and a proton, a free proton. Then you have also just some sodium floating around, and you're going to add an HCl sample, or just some amount of this strong acid HCl. So here the red part is the chloride part of the HCl, and the black part is the proton. So if you add this acid to the solution, normally what would happen is it would break apart. You would end up with some red halves and some black halves, which would be the free protons in the solution. But actually what happens is that you only get a tiny amount of free protons in the solution when you add the HCl. The other protons that the HCl dropped got picked up by a bicarbonate. So some of these blue halves here picked up a black half to form more carbonic acid molecules. So all three of these HCl's have dissociated after you added it. So you got just these three chloride halves. But their protons did not end up free in the solution. Only one proton ended up free in the solution. The other two protons combined with a bicarbonate to make a carbonic acid. So that's the way the buffer works. It's basically snapping up those extra protons so they're not free. They're not just floating around in the solution. They're bound up with something. So they're not affecting the pH unless they're free. If you were to add a base to this solution, on the other hand, kind of the opposite thing would happen. A base would normally try to snap up free protons, so it would take up this free proton here, and it would take up any other free protons that are in this water, and the pH would start going up. If that were to happen, then the buffer system will still act to prevent the pH from changing. And what's going to happen in that case is that some of these carbonic acids are going to dissociate and lose their free proton. Lose their proton so that it becomes a free proton. They're just going to drop their proton and turn into bicarbonates. So in that case, the amount of protons again will stay roughly the same, and the pH will not change very much. So the last kind of general aspect of chemistry that we'll talk about before we get into water more specifically is chemical functional groups. A functional group is a group of atoms that are attached to each other by various chemical bonds that kind of come up again and again in particular arrangements in different molecules. And we kind of especially talk about them with organic molecules. Organic molecules are carbon-based molecules. They always have carbon forming the backbone of the molecule. Carbon can make 4 bonds, so it's really kind of flexible in terms of how many things it can have attached to it. And so it's easy to form kind of a basic structure or skeleton of a molecule using just carbon. So an organic molecule would generally have some type of, basic structure or foundation made out of carbon, and then it'll have different functional groups attached to those carbons, and usually just some hydrogens attached to them also. So we'll go over a few of the more common functional groups to find in organic molecules that are relevant for biology. So first you have the hydroxyl group, which is an oxygen attached to a hydrogen. So that's shown in this diagram over here. The R represents the rest of the molecule, and the functional group is this oxygen with a hydrogen attached to it. So that's the hydroxyl group. A hydroxyl group is always polar because you have an oxygen attached to a hydrogen, and the oxygen is a lot more electronegative than the hydrogen is. So it's going to be kind of hogging the electrons towards itself, so that gives a polar covalent bond between the oxygen and the hydrogen, which makes the hydroxyl group polar. So since you have a partially positively charged hydrogen in there and a partially negatively charged oxygen, you can have hydrogen bonding also occurring with the hydroxyl group. So it could be involved in a hydrogen bond with another molecule. It's also a weak acid, which means that it has kind of a slight tendency to lose a proton in water. Then you have the carbonyl group, which is a carbon double bonded to an oxygen. So that is shown right here. These are a couple different examples of a carbonyl group. So one type of a carbonyl group has the carbon double bonded to the oxygen, and then it has also a hydrogen bonded to that carbon, and then just the rest of the molecule. Another version of the carbonyl group is kind of just the carbon double bonded to the oxygen, and then it has the rest of the molecule attached to either side of the carbon. So it would be kind of maybe in the middle of some larger molecule. The carbonyl group is also always polar because the bonds between the oxygen and the carbon are polar covalent bonds. And that again is because oxygen is a lot more electronegative than carbon is. Carbon has a similar electronegativity to hydrogen, and it's a good bit less than oxygen. So oxygen is going to be hogging the electrons in towards itself, which gives it a partial negative charge, and that means the carbon will end up with a partial positive charge. So the oxygen in the carbonyl group can also participate in hydrogen bonds because it has that partial negative charge on it. If you kind of put the hydroxyl group together with a carbonyl group, you get a carboxyl group, which has a carbon double bonded to an oxygen, and then also attached to that carbon is another oxygen with its hydrogen. So that is shown right here. Here's the carbon double bonded to the oxygen, that's the carbonyl part. Then also attached to that carbon you have another oxygen with a hydrogen on it, so that's the hydroxyl part. Both of them together are the carboxyl, and then you also have just the rest of the molecule attached to that carbon on the other side. So the carboxyl group, of course, is also polar. It has polar bonds in it between the carbon and oxygens and between the oxygen and the hydrogen. It also has atoms that can participate in hydrogen bonds, and it's acidic, which means that when you put it in water, it has a tendency to lose a proton. Another important functional group is the amino group, which is a nitrogen bonded to 2 different hydrogen atoms. So that's shown over here. You have the nitrogen with 2 different hydrogens attached to it, and then just the rest of the molecule also bonded to it, because nitrogen can form 3 bonds. So the amino group is also polar. You have a nitrogen bonded to hydrogens. Nitrogen is a lot more electronegative than hydrogen is. It's, nitrogen is also highly electronegative, like closer to how high oxygen is, and hydrogen is only moderately electronegative. So it's a good bit of difference in the electronegativities between nitrogen and hydrogen. So that gives you polar covalent bonds there, which means the amino group is polar. You have partially positively charged hydrogens and a partially negatively charged nitrogen. Those hydrogens can also participate in hydrogen bonds with another molecule because they have a partial positive charge. And the amino group is basic, which means that it has a tendency to pick up a proton when it is in water. An amino group and a carboxyl group can come together to form the backbone of an amino acid. So amino acids are kind of the basic molecule that proteins are made out of. A protein is basically just a chain of a bunch of different amino acids linked together and then folded up. So the amino acid is always divided into the backbone and the side chain. You have like 20 different amino acids that are important for human beings. They all have the same backbone, and then they each have a different side chain. The backbone is composed mostly of just the amino group and a carboxyl group. And then, of course, well, maybe not of course, but then also a central alpha carbon. So this is a diagram of a basic amino acid showing its backbone. The R is representing the side chain, so that would change depending on what type of amino acid we're talking about, but the rest of it, the backbone, would stay the same for all of the amino acids. So in this amino acid backbone, you have your central alpha carbon that the side chain is attached to. You also have another hydrogen attached to that central carbon, and then coming off either side of it, you have the amino group and the carboxyl group. So to the left of it, you have the amino group, and then to the right, you have the carboxyl group. The last two chemical or functional groups that we'll talk about are the phosphate group and the sulfhydryl group. So phosphate group is a central phosphorus atom with 4 oxygens attached all around it, and 2 of those oxygens will have a negative charge, so this is a functional group that has a charge. Here you have an image of the phosphate group. You can see the central phosphorus atom and then 4 oxygens arranged around it. The phosphorus atom can actually make 5 different bonds, so it's going to be double bonded to one of these oxygens, and then 2 of the other oxygens have just a single bond, and then they have a negative charge on them. And then the last oxygen is bonded to the phosphorus atom on one side and bonded to the rest of the molecule on its other side. So a lot of the time you might see multiple phosphate groups linked together on a molecule. The best example of that is ATP itself, which has 3 phosphate groups attached to it in a chain. So that means that this R would be another phosphate group, and then another phosphate group, and then the adenosine part of the ATP molecule. Whenever you have phosphate groups linked together like that, you end up storing chemical energy in them. The bonds between 2 phosphate groups are very high energy bonds in terms of the chemical energy that they store. So if you break those bonds, you're going to release a lot of energy that can be harnessed to perform other tasks in the cell. And that is essentially what is going on when the cell uses ATP to get energy to power some process. Finally, we have the sulfhydryl group, which is just a sulfur atom bonded to a hydrogen. So you can see that right here, the sulfur atom attached to the hydrogen atom, and then also attached to the rest of the molecule. There are a couple of amino acids that have the sulfhydryl group somewhere in their side chain, and if they get close together, those 2 sulfhydryl groups on the 2 amino acids can kind of react with each other to form what's called a disulfide bridge. So this is kind of showing that reaction. Here you have your 2 sulfhydryl groups that would be on perhaps 2 different amino acids. and they react together in a way that releases the hydrogens that were on them, and you end up having a bond form between the two sulfurs. So that's going to be a nonpolar covalent bond because, of course, sulfur has the same electronegativity as sulfur. So they're going to be sharing the electrons equally in that bond. So that's a quite strong bond in biology. Those disulfide bridges end up being pretty important for protein structure. A protein, as I mentioned, is a long chain of amino acids, but in order for it to have its function, it has to be folded up in the right way. So it has to have a specific 3D shape in order to do its function. And we'll go into this more when we cover proteins in our next chapter, actually. But for now, just, proteins have to have their shape in order to function. So here you have an example of a protein. This orange kind of ribbon here is the amino acid chain that is forming that protein, and you can see it is all kind of folded up to make this shape, which is necessary for the protein to have its function. So in order to stabilize this shape, a lot of proteins will use disulfide bridges. So here you have one amino acid at this point in the chain, and across the loop you have another amino acid at that point in the chain, and both of them have a sulfhydryl group, so those sulfhydryl groups can react to form the disulfide bridge. And this protein has multiple disulfide bridges kind of holding its loops together. So a lot of proteins will have disulfide bridges that are used for that purpose to kind of stabilize their structure. Okay, so now we've covered all of our chemistry basics, and we can get into the chemistry of water in a lot more detail. So we're going to talk about water in more detail because water is super important for life. So you might have heard that most of your volume is water. Actually, about 75% of the volume of any given cell is water. So yeah, you are mostly water. By volume, you're mostly just water. And, because of that, you really, really, really need to keep drinking more water. And, you're not going to last for long without taking in water. Because your cells really need to have that much water in them, or else they won't be able to function properly. Like, they can lose a little bit and get by, but if you have a cell that's more like 50% water, that cell is not going to be doing well. So for that reason, you cannot last a long time without water at all. Water is really important for life because it has a number of properties that are really useful for life. So first, water is known as the universal solvent, which means it kind of dissolves anything. It doesn't actually dissolve anything, of course, like it won't dissolve oil, but it dissolves a remarkably wide range of things. So we call it the universal solvent. The reason why it is the universal solvent is because it is a small molecule and it's very, very polar. So those two properties allow it to behave as a solvent for many different compounds. Water is also important for life because it's a really good insulator, which means that it kind of prevents temperature from, changing. Yeah, so water will just kind of hold on to its temperature, whatever it is, and it takes a lot of energy to change the temperature of water, which means that organisms can use it as insulation. The reason why water is so good at insulating is because it extensively hydrogen bonds with itself. Water also has really high surface tension, which is important for life. Not literally every life form is relying on the high surface tension of water, but a lot of different life forms do. Water has really high surface tension, again, because it forms extensive hydrogen bonds with itself. And that surface tension just means that it's kind of hard to break the surface of water in a way. Like if you push on it, it pushes back on you. So of course you can do it, but if you have something that's light, you can actually balance it on the top of a surface of water. And then finally, when water is solid, so when it's ice, it actually is less dense than when it's a liquid, so it will float, or ice will float on top of liquid water. So that's not really normal. Usually if you have a solid substance, it's going to be more dense than the liquid version of that substance, and it would sink. But for water, it's the other way around. Ice is less dense and it floats. And that's also extremely important for life, well, in particular for any type of life that is living in the water. And again, the reason why ice floats is because water will extensively hydrogen bond with itself. So that's kind of our overview of the properties of water that are crucial for life. We're going to go through these one by one and talk about how the chemistry of water gives rise to these properties and why they are important. So we'll start with the basic structure of water, which we've kind of already gone over a bit. We're just kind of review that here. So water is a oxygen atom with two hydrogen atoms covalently bonded to it. Because oxygen is highly electronegative and hydrogen is only moderately electronegative, that means that those are going to be polar covalent bonds between the oxygen and the hydrogen, in which the electrons are being pulled towards the oxygen side of the bond, and they're kind of just spending more time with the oxygen and spending less time with the hydrogens. So both the oxygen and the hydrogen are tugging on the electrons that are in those covalent bonds, but oxygen is just able to pull harder, and hydrogen cannot pull that hard, which means that oxygen is going to pull the electrons over to its side of the bond, kind of leaving hydrogen out in the cold. So that's going to mean that oxygen has like kind of extra electrons almost, because the electrons are closer to it, and that will give it a partial negative charge. Whereas hydrogen, on the other hand, is almost missing electrons since the electrons are quite far from it, so it ends up with a partial positive charge. So let's see, this diagram here is illustrating that. You have your oxygen and your two hydrogens attached to it. These arrows are those polar covalent bonds between the oxygen and the hydrogen, and then the dots are the electrons. So these electrons in these polar covalent bonds are closer towards the oxygen and further from the hydrogen because oxygen is more electronegative than hydrogen by a good bit. So since these electrons are spending more time with the oxygen, you end up having partial negative charges on the oxygen. Since they're spending less time with the hydrogens, each of these hydrogens ends up with a partial positive charge. So these are polar covalent bonds in which the hydrogen is partially positively charged and the oxygen is partially negatively charged. Then you also have these two pairs of electrons on oxygen that are not involved in any bond, and those are going to push the hydrogens over to one side of the molecule, which is kind of shown in this diagram here. So here you have your two pairs of electrons that are not involved in a bond that are attached to the hydrogen, to the oxygen. And then you have your electrons that are involved with bonds with hydrogen. These electrons are getting pushed off to one side by these other paired electrons. So that means that the hydrogens are both coming off the same side of the oxygen, and the molecule is kind of shaped like a triangle in a way. Or maybe like a boomerang, but you know, it's kind of got that triangular angle to it, in which the hydrogens are both on the same side of the molecule. So since those hydrogens that both have the partial positive charge are on one side of the molecule, and since on the other side of the molecule you have the oxygen with its partial negative charges, that means that when you're looking at the whole molecule, you have one partially positive side and one partially negative side, and that means you're looking at a polar molecule. So water is really, really polar because it basically just has that oxygen with partial negative charges and those two hydrogens together on a side with partial positive charges. Most polar molecules don't have kind of that big of a difference in the charge on either side of the molecule. Then finally, because you have those polar covalent bonds in water, and you have your partially positive hydrogens and your partially negative oxygen, that means that you have basically every atom that is in the water is able to participate in a hydrogen bond. The oxygen can do it because it's partially negative, and the hydrogens can do it because they're partially positive. So if you had another water molecule nearby, which you probably usually do, since you don't usually find a single water molecule like literally by itself, those water molecules will be able to hydrogen bond with each other. So you could have the partially positive hydrogen on one of them, hydrogen bonding with the partially negative oxygen on the other water molecule. So the fact that the water molecule is so polar and just has those polar covalent bonds with partially negative oxygen and partially positive hydrogens, that's the reason why it's able to hydrogen bond with itself. So before we talk more about the hydrogen bonding of water with itself, let's talk about its properties as the universal solvent. So you may have heard kind of the general rule of thumb for determining if one thing will dissolve another thing is like dissolves like. So that means that chemicals that have similar properties can dissolve each other, and chemicals that have very different properties probably cannot dissolve each other. So that means that anything that is similar in some way in terms of its chemical properties to water would be dissolved by water. Anything that's different wouldn't be dissolved by water. Water is a polar molecule with partial charges on it. So it's able to dissolve anything that has a charge or a partial charge on it. So anything that has a charge or anything that's polar could be dissolved by water. Only things that are not polar at all cannot be dissolved by water. And kind of the way that it would work would be that if you put something in water, something that is charged or partially charged, you're going to have the partial charges on the water being attracted to the charges or partial charges on this molecule that you've put into the water. And the water molecules will just kind of tug on the molecules that you have put in and pull them apart and surround them with water molecules. And at that point, it is a dissolved substance. So here you have an example of table salt dissolving in water. So table salt is just sodium chloride. The chloride has a negative charge. The sodium has a positive charge. If you put this in water, you're going to have these chlorides with the negative charges being attracted to the positively charged or the partially positively charged hydrogens on water. Those hydrogens are just going to come in and start making little tugs on this chloride until it kind of dissociates or separates from the rest of the salt molecule, and at that point is going to end up surrounded on all sides by water molecules that are all arranged so that their hydrogens are pointing in towards the chloride, since positive attracts negative. The same thing will happen to the sodium, except that it's going to be the oxygens that are interacting with it. So the oxygens on water are partially negatively charged. They're going to be coming in and tugging on the sodium atoms in the grain of salt, since they have a positive charge on them. When the oxygens on the water molecules manage to tug a sodium off, they're going to surround it with a shell of water molecules in which all of the molecules are arranged so that their oxygen side is pointing in towards the sodium. So the sodium has a positively charged or a positive charge, and the water molecules will always face it with their partially negatively charged side, which is the oxygen side. So the water is just going to pick this grain of salt apart atom by atom by atom until all of the atoms have been pulled apart from each other and surrounded by water molecules. And it's able to do that because it has the partial charges that are able to interact with these charged atoms in the table salt. On the other side here, you have a similar example with a molecule that is not charged, but instead it's polar. So this is glucose in the center here. Glucose has a ring of carbons that are shown in black, and it also has a bunch of oxygens coming off of those carbons and little hydrogens attached all over it wherever they can fit. So a lot of these carbons and oxygens have a hydrogen attached to them. Anytime you have oxygen attached to a hydrogen, well, this would be the oxygen actually, in white you have the hydrogen. That is a hydroxyl group. That is a polar group in which the oxygen will be partially negatively charged and the hydrogen will be partially positively charged. So this glucose has a bunch of partially positively charged hydrogens sticking out all over it, and those are going to be able to interact with the water by forming hydrogen bonds. So you're going to have water molecules coming in, their partially negative oxygen is going to be attracted to the partially positive hydrogens on these glucoses, and you're going to have hydrogen bonds forming. So the water molecules, since they're so small, if you were to put kind of a grain of sugar, because glucose is a sugar, if you put a grain of sugar in some water, you're going to have these water molecules that are really tiny, kind of inching up into that grain of sugar, hydrogen bonding with the partially positive hydrogens on the glucose within the sugar wherever they're able to, and eventually they're going to end up surrounding a glucose molecule enough to kind of pull it off of the main grain of sugar, and they will slowly take the sugar apart piece by piece glucose molecule by glucose molecule, just like that. This is going to be a much slower process, so as you probably know, when you put sugar in some water, it does dissolve, but it doesn't dissolve super fast like the way that salt does. So it is harder for water to dissolve the sugar, but it can still get it done if you wait for long enough or, stir hard enough. So that's the basic way in which water is able to dissolve things. It can do that with anything that has a partial charge or a full charge. It's always based on the interaction or the attraction between the partial charges on the water and the charges or partial charges on whatever molecule the water will be dissolving. The only thing that water cannot dissolve at all is something that is non-polar, that doesn't have a charge and doesn't have a partial charge anywhere on it. So an example of a substance like that would be oil. If you put oil in water, of course, it's not going to dissolve in the water. The water actually has nowhere that it would be able to interact with the oil on because there are no charges or partial charges on the oil molecules. So that situation is kind of shown in this image at the bottom right of the slide. So here you have oil molecules. Oil is basically a chain of carbons with hydrogen stuck onto them. Since carbon and hydrogen have about the same electronegativity, they're always going to make non-polar covalent bonds with each other. So these molecules have nothing but non-polar covalent bonds. They have no charges or partial charges anywhere on them. When you put them in water, the water molecules will always be interacting with each other because they're always going to be attracted to the partial charges on other water molecules. So you see all these kind of dashed lines in here. Those are hydrogen bonds that the water molecules are forming with each other. It's always just the partially positive hydrogen on one water molecule interacting with the partially negative oxygen on another water molecule. So these water molecules are all interacting with each other busily. They have no way to interact with the oil molecules at all, so they will end up kind of freezing the oil out almost. They're all just too busy interacting with each other, and the oil molecules end up just clustered together with no one that will interact with them, and so they're not going to dissolve. So we have a couple of words to describe things that do and don't dissolve in water. A hydrophilic substance is any substance that can dissolve in water, and a hydrophobic substance is any substance that cannot dissolve in water. So salts and sugar, those are hydrophilic substances. They have charges or partial charges. They can dissolve in water. Oil is a hydrophobic substance with no charges or partial charges, so it does not dissolve in water. If you look at kind of the etymology of those words, hydrophilic and hydrophobic, you can break them down into their Greek roots. Hydro means water, then philic means loving, so hydrophilic means water loving. Something that's water loving, I guess, gets dissolved by the water. Then for hydrophobic, phobic means fearing, or phobia is like a fear. So hydrophobic means fearing water, or water fearing. So something that is hydrophobic, when you put it in water, instead of interacting with the water, it's going to huddle by itself and not interact with the water at all and not be dissolved by that water. So now we'll get into the other characteristics of water that are important for life, and all of them are based on hydrogen bonding. So we'll take a moment to understand more about how hydrogen bonds occur in water molecules. So every time that you have a hydrogen bond between two water molecules, that means that it's the partially positive hydrogen on one water molecule that is attracted to the partially negative oxygen on another water molecule. So that is shown right here. You have two water molecules here. Here you have the partially positive hydrogen on one of those water molecules. Here you have the partially negative oxygen on the other water molecule. Since negative attracts positive, these partial charges will be attracted to each other, and that kind of forms a weak interaction between the partially negative oxygen and the partially positive hydrogen that we call a hydrogen bond. So this interaction is very weak. It's very easy to break it, but it ends up being significant because when you have a sample of water, you're just going to have like a lot of these hydrogen bonds in there. One of them is weak, but together, if you get a lot of them, they can be pretty strong altogether. It's just like well, I guess they don't really have phone books anymore, but you know, if you have a ancient times phone book somewhere in your house, if you have two of them actually, if you interweave the pages of the phone books and then you try to pull them apart, you can't do it. So, you know, the amount of friction that you have between, you know, any two pages that are interweaved with each other is very, very little. It's very easy for you to pull it apart without any real effort. But if you add up all the friction between all the different pages of the phone books, that gets to be quite a lot of friction, so that you're actually probably not strong enough to pull those phone books apart. So the fact that water molecules are able to hydrogen bond with each other like this kind of makes them just like sticky. They just kind of have this tendency to stick to each other using these weak interactions between their partial charges that we call hydrogen bonds. The fancy word for that stickiness is cohesion. So cohesion is the attraction of water molecules to each other that's based on the hydrogen bonding that they do with each other. Here you have an image of a water molecule in the center, hydrogen bonding with other water molecules around it. So on the top you have this partially positive hydrogen making a hydrogen bond with the partially negative oxygen on another water molecule. Here the other partially positive hydrogen on that first molecule is hydrogen bonding with the partially negative oxygen on another water molecule. And then the oxygen on this central water molecule actually has two partially negative charges on it, one for each of the polar covalent bonds that it is involved in. So it's able to form not one hydrogen bond, but two. So it can bond to two other partially positive hydrogens on two different water molecules, which means that the maximum amount of hydrogen bonds that any one water molecule can form is 4. It can form 2 with its partially positive hydrogens and 2 more with its partially negative oxygen because it has 2 partially negative charges on it. That's kind of the maximum amount of bonds that could be formed by water. Usually when you have water, you know, just like in a sample of water, it's not going to be any one molecule in that water would not be making all 4 potential hydrogen bonds that it could. It's going to be making maybe 1 or 2 or 3 at the most, probably not 4, unless it's very, very cold, which we'll talk about in a moment. But so it could make up to 4, but it usually would be making fewer than that. And here you have an image of an actual larger sample of water, kind of with a lot more water molecules in it. So you can see that they're all just hydrogen bonded with each other willy-nilly. You have a lot of them, they're involved in kind of 2 or 3 hydrogen bonds, and they're all attached to each other some way or somehow. So in actual real life, these molecules are all going to be kind of tumbling past each other, depending on the temperature of the water. So the higher the temperature of the water is, the faster its molecules will be moving, and the faster they would be tumbling past each other. And as they're moving around, they're going to be having these hydrogen bonds kind of broken and then remade. So if this particular water molecule starts tilting as it tumbles, tumbles through the water, it's going to maybe break this hydrogen bond right here, but it'll form another one later on. So you'll always have this kind of shifting mass of all these different water molecules moving through the water and forming hydrogen bonds with each other, breaking hydrogen bonds, forming new ones. At any given time, you have a bunch of hydrogen bonds in here. Any one of them is quite weak, but if you're looking at all of them together, it's so many of them that they end up to be kind of a significant amount of force holding the water together. So the first characteristic of water that's based on hydrogen bonding that we'll talk about is surface tension, because it's kind of the least important one, I think. Although that could probably be debated actually, but we'll just go with it. I think it's the least important in my personal opinion. Surface tension is the ability of a sample of water to kind of resist changes in the shape of its surface, so that if you push down on the water, it will push back on you. Of course, you're very strong, so you can break the surface of the water. But if you were small, like an insect, like this little water crawler guy, then you're actually not heavy enough to break the surface tension of the water. and so you can basically end up walking on the water. Water actually has one of the strongest surface tensions that any known liquid has. So, every liquid has a surface tension. A lot of them have a very small surface tension, so it's really, really easy to break the surface, and some of them have a higher surface tension, and water is like one of the highest. And that is because of hydrogen bonding that occurs, especially at the surface of the water, or between water molecules that are at the surface. So when you have a water molecule at the surface of the water, it's kind of limited in the directions in which it can make hydrogen bonds with other water molecules because there's no more water above it. If you're a water molecule that's kind of like down deep, like say we have a glass of water and you're a water molecule that's kind of down deep in that water in the glass, you can hydrogen bond anywhere. Like on all sides, in all directions, there's other water molecules that you could potentially hydrogen bond with. So you're going to be hydrogen bonding in all directions equally. If you're at the top of that glass of water, though, then there's water, on either side of you, and there's water below you, but there's no more water above you because you're the top molecule. So if you're going to make a hydrogen bond, it has to be with someone to either side or below you, but it can't be with someone above you. You're limited in in the directions in which you could form hydrogen bonds, which means that those water molecules at the surface are going to end up forming more hydrogen bonds with molecules to either side, compared to water molecules anywhere else within the water. So that's kind of shown in this diagram right here. Here you have water molecules, a line of them at the surface of this sample of water, and then you have water molecules that are down below. These water molecules that are below can hydrogen bond in any direction, but the ones that are on the surface can only hydrogen bond side to side or down below. So they're going to end up forming extra hydrogen bonds side to side, and some extra ones down below as well. These extra side-to-side bonds, though, are the ones that are really important for the surface tension. It just means that the connections between these water molecules that are forming the surface is kind of stronger than the connections between other water molecules in the liquid. There's just more hydrogen bonds there at the surface, holding that surface together. So again, any one of these hydrogen bonds is very weak, but when you have a lot of them together, it makes quite a strong force. So that means that the surface of the water is kind of held together by these extra hydrogen bonds, and that makes it hard to disrupt those molecules. So if you were kind of trying to push down onto this water, you might be trying to push this molecule down further because maybe your finger's coming down right here. In order to do that, you're going to have to break these hydrogen bonds that this water molecule is making with other molecules on either side of it. And since there's more of them than you would normally have, then it's just going to be harder for you to do that. Of course, you'll be able to do that, but something that's way, way smaller and weaker than you probably might not be able to do that, like an insect. Another consequence of surface tension in water is the fact that water forms droplets. So if you have just a small bit of water, the surface molecules of the water will be pulling on each other, and they'll be attached to the molecules that are further into the sample, and they'll end up just pulling everything into a sphere, into the shape of a droplet. That's kind of the shape that water can form, in which it'll have the most hydrogen bonds at its surface, and this kind of the most strongest, stablest shape that it could form. So if you didn't have that surface tension, that extra interaction between water molecules at the surface, then you actually wouldn't have droplets forming from water. And those droplets actually end up being important for certain organisms. So here you have kind of a summary of some of the organisms that find an importance in surface tension. So first you have certain insects, like the spider, that are able to walk on water because of that surface tension. So here, the surface tension of the water, the hydrogen bonds between water molecules at the surface here, is actually creating a stronger force than the force that this spider generates pushing down on the water when he steps on it with his legs. So he's actually not heavy enough to break the surface tension of the water, and he is supported on the surface. So there's actually a number of insects that rely on surface tension in order to walk on water, and that ends up being important for their kind of way of life. You can actually also balance a paperclip on water if you put it carefully enough. Like, so if you're kind of ginger and careful enough when you're placing it, you can rest a paperclip on water. Here you have a water droplet bouncing, so you can see the surface tension is actually the thing that is holding this droplet together. The reason why it doesn't all just splash apart when it hits the surface is because the hydrogen bonds between molecules at the surface of the droplet are actually stronger. They have more force than the force with which the water droplet is hitting the surface, so it will remain kind of cohesive. And here you have more droplets that, again, they form only because of the surface tension of water. So there are certain organisms that rely on having these droplets in order to get their water, or carry out some aspect of their life strategy. And then finally, from surface tension, we get capillary action, which is necessary for trees and any large plant. So capillary action, which we'll talk more about in a moment, but it is what allows a tree to carry water up from the ground, up its trunk, up all its branches to the leaves that actually need the water. Without capillary action, the tree would not have any way of transporting water from the ground all the way up to its tippy top leaves, and trees would basically not exist, and no plant would be able to get particularly tall. Okay, so capillary action is basically the ability of water to climb up through a narrow passageway. It has to be a passageway where the walls of the passage are made out of some substance that the water is attracted to. So something that's polar, something that's partially charged, something that's charged. It can't be something that's completely nonpolar. So an example would be maybe a paper towel. So we've probably all had the experience of dipping like a little corner of a paper towel into water, and you can watch the water climb up into the rest of the paper towel. That is actually capillary action. You have a lot of tiny passageways through that paper towel, and the water is climbing up them. Also, if you dip a paintbrush into paint, water will actually climb up between the fibers of the paintbrush if you're using a water-based paint. And of course, in plant veins, they are just little passages that water is climbing up to get from the roots of the plant to the leaves. Capillary action is caused by the interaction between adhesion and surface tension of water. So cohesion is how water molecules are able to stick to each other because of hydrogen bonding between each other. Adhesion is how water molecules are able to stick to other molecules. In this case, that would be the molecules that are making up the walls of the passage that the water is going to be climbing. So again, if it's something that is charged or partially charged, something that's polar, the water molecules will be able to interact with it. They will adhere to it. You will have adhesion between those water molecules and the molecules of that passage, and the water will therefore be able to climb up it. So you're going to have a few water molecules that are kind of just at the wall of the passage that are sticking to the wall based on their adhesion to the wall. So it's going to be, some sort of charge-based attraction between these water molecules and the molecules making up the passage wall. They will end up kind of climbing a little ways up the wall just by sticking to it. And then you're going to have surface tension between those water molecules and the other water molecules at the surface. And of course, just the general stickiness of water molecules to each other, pulling the rest of the water up, following those molecules that are sticking to the wall of the passage. So you can see that happening here at the wall of this passage. You have a few water molecules that are sticking to it. They end up climbing up a little ways because they stick to it, and they're going to pull other water molecules up behind them. In this case, this passage is a little too wide for capillary action to work. It can only work on a narrow passage. So you have kind of the sides or the edges of the water here climbing up the walls, but the whole column of water is not going to rise. Here you have a passage that is more narrow, so as you have some molecules sticking to the sides of the passage, they're going to have also surface tension, or extra hydrogen bonding with the molecules behind them on the surface that pulls those molecules up, and it's all going to start rising, and then the molecules at the surface are going to be hydrogen bonding with the molecules down beneath the surface and pulling them up as well. Everything is going to end up being pulled up through the passage, and the water will rise in the passage by capillary action. It's going to keep going up until the total mass of this risen water is too much, and then all these hydrogen bonds that are kind of holding this whole thing together kind of break, and it would, at least it'll remain at, remain at its max level. So here you have kind of a graphic showing capillary action in the veins of a plant. So here you have, basically the veins within a plant. These are the little passages that water would be climbing up through by capillary action. And the blue dots are, of course, the water molecules. If you were to zoom in on them, you might be able to see their interactions with each other and with the walls of those passages. So this water molecule that is contacting the wall is going to be interacting with it by adhesion. You're going to have maybe some partial charges in this wall that are attracting the water molecule, so it kind of grabs on there. It also is going to be hydrogen bonding with the water molecule in front of it and the water molecule behind it, and it'll be kind of moving up. As this water molecule above it moves up a bit, it's going to tug this one up, that's going to tug this one up, that's going to tug this one up. So these hydrogen bonds that they have with each other are kind of what's going to make sure that the whole column of water starts rising. And you'll get, a whole little column of water rising up all the way, maybe from the roots of a plant to the tippy top of a tree. Then finally you have animals that rely on capillary action and or water droplets to be able to drink. So first you've got a number of lizards that have kind of horns all over them. On the top here you have a lizard called the thorny devil from Australia, and then below him, of course, a horny toad from around here. So these lizards are covered in these kind of spikes that are actually not just used for defense, but they're used to collect water. So as dew forms in the morning, it'll actually form droplets on all these little spikes. And then you also have, you can't really super see it, but you have like little rivulets or passages, kind of little cracks in the lizard's skin, little channels basically that are formed that will funnel water into the mouth. So water will collect on all these spikes, forming droplets, and then it will move by capillary action into these little channels on the lizard's skin and will be delivered to the corner of the lizard's mouth where it can drink it. Same thing happens for this horny toad here. It's collecting water on all these droplets, and you have little channels in his skin that funnel the water in towards his mouth so he can drink it. On the bottom here you have a Namib desert beetle from Africa that has a pretty similar strategy. So it actually has tiny little bumps and ridges on its butt here, and it will go out into the kind of morning mist and stick its butt up into the mist, and water will condense on these ridges, and it will flow down the beetle's body until it collects at his mouth, and it forms a droplet at his mouth instead of just running off into the sand because of its very high surface tension. So if water didn't have a high surface tension, it wouldn't be, it would just run off his body into the sand. It wouldn't be collecting in a droplet at his mouth that's convenient for him to drink. Then finally, these birds here are sand grouse. So whenever these sand grouse have their young, those young need, a good amount of water, but they don't want to make their nest too close to a watering hole. These birds live in the desert, so they have to get their water from a watering hole. They don't want their nest to be too close to the watering hole because, of course, there's also predators at the watering hole, so it's a dangerous place to have a nest. So they'll actually make the nest pretty far from a watering hole, just out in the desert somewhere. And the mom will kind of stay with the babies, and then the dad will fly to a watering hole and just sit in it and let water move up into his feathers. So water is actually going to be soaking up into the feathers of this daddy sand grouse by capillary action. He's going to soak there until his feathers are full of water, then he will fly back to the nest, and the babies will drink the water from his feathers. So without capillary action, this bird would, have to find a completely different way of living its life. Another characteristic of water that's really important for living things is its ability to buffer temperature, or just resist changes in its temperature and act as a good insulator. Water is able to do that because it has a very high specific heat capacity. The specific heat capacity is how much energy you have to add to a substance, to 1 gram of a substance, in order to increase its temperature by 1 degree Celsius. And since temperature is the average movement of molecules in that substance, when you say you're going to increase its temperature, that means you're going to speed up the movement of those molecules that it has. So if you have a low specific heat capacity, that means that it does not take a lot of energy to raise the temperature of whatever substance you're made of. If you have a very high specific heat capacity, like water does, that means that it takes a lot of energy. You have to put a lot of energy into that substance if you're going to increase its temperature. So if you have a body of water, maybe it's like a lake or a pond, and the sun is shining down on it, you are adding energy to that water, right? The sun's rays are hitting the water and heating it up. So that energy is being absorbed by the water. But actually, before the energy from the sun can actually heat the water up by increasing the movement speed of the water molecules, first you have to break the hydrogen bonds between those water molecules. So some of the energy from the sun first has to go into breaking hydrogen bonds, and then once the hydrogen bonds are broken, then the water molecules can move faster. So only after you've broken the hydrogen bonds can you actually put energy towards, moving the molecules faster and heating the water up. So that means that hydrogen bonding of water molecules to each other is the reason why water has such a high specific heat capacity. It's the reason why it takes so much energy to increase the temperature of water, and that's the reason why it is a good insulator. It's also really good for a coolant. Water is actually the coolant that is used in nuclear reactors. So you'll have, the nuclear reactor kind of with its reaction going on, and basically the difference between that and a nuclear bomb is that it's happening slowly. It's not happening all at once. The fuel isn't being consumed all at one time. It's happening more slowly. So in order to keep it happening slow, you have to keep the temperature controlled, and that is done using giant basins of water, basically, that are all around this reaction. So they're not using water there because it's cheap. They're actually using it because it is the best substance that is available that they would be able to use. It is one of the best insulators around. So the fact that we are mostly water is really useful for controlling our temperature. If we were mostly made out of some substance that had a really low specific heat capacity, then it would be very easy for our temperature to change when we walk out into the sun, or walk into a cold room or something like that. The fact that we're mostly made out of water means that you have to kind of put a lot of energy into us in order to change our temperature. So that just kind of helps us maintain our body temperature at the level that we need it to be. Also, for organisms that are living within a body of water, it's really useful. It helps kind of buffer the temperature of their environment. So if you're like a fish living in a pond, outside you might have some crazy hot days or some cold days, but inside the pond it's always going to be about the same temperature, since the water is very resistant to changing its temperature. Of course, in the early Earth, you had some really harsh conditions on kind of the land, and you had a lot of radiation. In the early Earth, there actually wasn't an ozone layer yet to protect us from radiation, and so it was actually the oceans and the water of the oceans that was protecting organisms from the really harsh temperatures and from the radiation and everything going on in the Earth's environment at that time. Related to the specific heat capacity of water, you also have the heat of vaporization of water. The heat of vaporization is how much energy you have to put into a substance, into 1 gram of a substance, to convert that substance from a liquid to a gas. So how much energy do you have to put into 1 gram of water to take it from liquid water to steam, which is the gaseous form of water? For water, it's a very high amount of energy. So just like the specific heat capacity of water is high, its heat of vaporization is also really high. And both of them are high for the same reason, because of those hydrogen bonds between the water molecules. So because water has such a high heat of vaporization, that means that you can actually use it to cool stuff down by evaporating it. So when we sweat, we put water onto the surface of our body, and you're going to have some of the energy, some of the heat energy in the body drawn off into that sweat, and it'll make the sweat evaporate. So because water has such a high heat of vaporization, your sweat has to absorb a lot of heat energy from your body before it's able to actually convert to a gas and evaporate. That means that it draws off a lot of heat and is really effective for keeping you cool. That's also the principle based on which swamp coolers work. Of course, they only work if it's not humid outside, because, if there's too much water in the air already, then it's not going to evaporate no matter what. But you can actually see this in action if you kind of just wet your hand, like get some water on your hand, and then just kind of wave your hand quickly through the air, kind of act like your hand is a fan and you're fanning yourself. You'll notice that your hand begins to get really cold as all that water on your hand starts to evaporate. It can only evaporate by drawing off heat energy from your hand. So this diagram is kind of showing how water acts to insulate temperature. So here you have the ocean and a beach, and it's a hot sunny day. If you were to measure the temperature of the sand and of the ocean, you would notice that the sand is getting hotter and hotter as the day goes on. As more and more sun energy beats down on that sand, it's absorbing a lot of energy, and its temperature is going to go up pretty high. But if you have a thermometer and you're measuring the ocean water itself, you're going to notice that the temperature doesn't really rise throughout the day. Maybe rises a tiny bit, but not really very much at all. It remains kind of nice, cool water, even though the sand is getting super hot. So that's, again, because water has such a high specific heat capacity. You have to add a lot of energy to it to increase its temperature, and that is because of hydrogen bonding. So as the sun's rays are hitting the water, if you were to zoom in, you would actually see hydrogen bonds being broken by the sun's rays. So first the energy of the sun goes into breaking these hydrogen bonds, and then it can go into making the water molecules move faster. But if you're looking at the whole kind of sample of the water in the ocean, you're going to notice that there's a bunch of water molecules that are all making hydrogen bonds with each other. And here these bonds are color-coded, so the red ones are broken bonds. So these are bonds, hydrogen bonds that have just been broken by the energy from the sun's rays. And then in blue here you have newly formed hydrogen bonds. So even after the sun breaks one of these hydrogen bonds, this water molecule is just going to tumble away and make a new hydrogen bond with the next close by water molecule that it finds. So every time the sun is breaking a hydrogen bond, a new one is forming, and it has to break them, all of them, before it can actually increase the temperature. And that's like never going to happen. So it would at least have to be breaking hydrogen bonds at a rate that's quicker than the rate at which they're reforming in order to significantly increase the temperature of this water. And that takes really a truly massive amount of energy to break all of those hydrogen bonds and the new ones that form. The fact that water is so good as an insulator, is so good at buffering temperature, doesn't just affect organisms that are kind of living in water or that have water in their bodies, on an individual level. It's actually affecting the global climate as well, and also the local climate next to a body of water. So if you're living next to a body of water, maybe like a really big lake or something, during the daytime, the air over the lake or over the water is going to be cooler than the air over the land. So the air is being heated by the sun, but it's also being heated by the surface underneath it. So this land is getting really warmed up by the sun. Its temperature is increasing a lot. Some of that increased temperature is going to kind of bleed off into the air above it and heat up that air. So that gives you warm air above the land. Above the water, you have the sun's rays heating the water up, heating the air up, but you also have the water cooling that air down, because the water itself isn't really changing its temperature very much, so it's going to stay cool, and any air that's above it is going to kind of lose some of its heat to the water and cool down. Then warm air will always rise and cool air sinks. So the warm air that's over the land is going to end up rising up further up into the atmosphere. The cool air that was over the water is going to sink down and be drawn into this wake of the warm air. So you end up having a kind of like a circle or an oval where warm air from the land is rising up and moving out to the water. Cool air over the water is sinking down and moving into land. So this means that if you're actually on the land, you're going to be experiencing this cool sea breeze or cool lake breeze. So the cool air coming in off of this body of water is going to be, cooling things down and making things nicer for you overall. Overall, this land here is going to not get quite as hot as it would otherwise because it's got this cool air from the water body moving into it, and that ends up cooling it down a bit. When it's nighttime, the opposite thing is going to happen. So as the sun's energy goes away, the land is going to start losing its temperature pretty quickly and it's going to get cold. The air above it is going to be similarly cold. But on the body of water, it's actually going to hang on to its temperature. Its temperature just doesn't really change very much, when you have energy being input into it or taken out of it. So it's maintaining its temperature. This water is going to be warmer now than the land is. The air over it is also going to end up being warmer than the air over the land. So this warmer air over the body of water is going to rise up into the sky, higher into the atmosphere, and end up moving into the land. The air that's over the land that's cooler is going to sink and end up moving out onto the body of water. So now you have warmer air coming onto the cooler land. That's going to end up warming the land up just a bit. So it's going to end up not being quite as cold as it would be otherwise. So the upshot is, if you're living by a large body of water, the days are going to be cooler than they would be otherwise, and the nights are going to be warmer than they would be otherwise. Overall, the temperature here is going to be more moderate next to the water than further away from the water. Another example of water moderating climate or influencing climate would be kind of ocean currents, and in particular the Gulf Stream. So here you have the Gulf Stream current. It flows from Florida all the way across the Atlantic Ocean, heading north until it hits the UK. So if you're looking at the latitude that the UK is at, it's actually pretty high. It's basically at the same level that Canada is. So it's as far north as Canada. And of course, Canada is really cold. A lot of Canada is actually covered in ice for basically, most of the year. It's a very cold place. The UK is not that cold. There are no parts of the UK that are always covered in ice. It's a nice green temperate place. That's actually because of this Gulf Stream current. So if it was just about the latitude that it's at or how far north it is, then the UK would be as cold as Canada is, but it's a lot warmer than that. And that's because it's getting this warm water from the Gulf Stream. So when this water is coming up from Florida, it's pretty close to the equator, not too far above the equator. This is pretty warm water. As it comes up in the Gulf Stream current going north, it enters these colder waters, but it doesn't lose its temperature that much. You're still going to have warm water up here coming in the Gulf Stream, carried up from the south. Because it's so hard for water to change its temperature, this warm water is going to maintain its temperature as it comes from Florida all the way north across the Atlantic to the UK. So now you have a warmer coast here by the UK than what you have in Canada. I guess this kind of black color here of the water by the coast in Canada is indicating that that is really, really cold water. This blue color by London or by the UK is showing that, you know, I mean, it's not like warm. It's cool, but it's not cold. It's not crazy cold. That means that overall, the whole kind of UK landmass is going to be warmer than it would be because it's getting this warm water on its coast. Okay, so the last characteristic of water that's important for life that we need to talk about is the density of ice. So for almost any substance that you would think of, the solid form is going to be denser than the liquid form, which means that the solid is going to sink in the liquid. It should always be that like the gas is the least dense, the liquid is medium dense, and then the solid is the most dense form of that substance. But water doesn't work like that. So gaseous water, which is steam, is actually the least dense state of water, but the liquid is more dense than the solid form, which is ice. So liquid water is more dense than ice. That means that ice is going to float on top of liquid water. Actually, as the water reduces in its temperature, it will get denser and denser and denser until just before it freezes. Actually, water would freeze at 0 degrees Celsius, and at 4 degrees Celsius is its densest point. So if it goes lower than 4 degrees Celsius, then it's going to get less dense again until it actually forms ice, which is less dense than any liquid water, and so it floats. And this is an image of water molecules in ice. So you can see they have a very regular structure. They're arranged in this kind of repeating pattern, and you have hydrogen bonds between the water molecules in the ice. It's actually that repeating pattern and the hydrogen bonds that are holding them, well, I should say it's the hydrogen bonds that are holding them in that repeated pattern. And you can see that this is not a very dense pattern. There's these kind of giant hexagonal holes in it that are filled with just nothing. And that is the reason why ice is not that dense compared to liquid water. So this is kind of showing the same thing. But if you're talking about a sample of liquid water, you're going to have those molecules moving around, tumbling past each other. They're all going to be hydrogen bonding with each other. None of them will be making the maximum amount of hydrogen bonds, or very few of them will be making the maximum amount of hydrogen bonds. And those bonds will constantly be broken and reformed. So all the time you have molecules of water tumbling past each other, breaking hydrogen bonds as they move past each other, forming new ones as they get closer to each other. Those new bonds break again as the molecules move further away from each other. So this process of making and breaking hydrogen bonds is occurring over and over and over again in liquid water. As the temperature of the water goes down, that means that the movement speed of those water molecules is going to go down. So now they're tumbling more and more slowly. When they're moving really slowly, now it's harder to break those hydrogen bonds when they form. It's easy to break a hydrogen bond when you're moving really fast, but if you're moving pretty slow, then you don't have as much energy associated with your movement, and it might not be enough energy to break the hydrogen bond. So you might not be able to tumble past the water molecule that you're hydrogen bonded with. You might just be stuck there. So as the temperature drops, the molecules move more slowly, and you have fewer hydrogen bonds breaking. More of them are going to be forming, and less of them will be breaking, which means overall, the average number of hydrogen bonds that any water molecule is involved in is going to be going up as the water temperature goes down. Then eventually, just before the water actually freezes into ice, the temperature is so low and the molecules are moving so slowly past each other that you basically don't have hydrogen bonds breaking at all. Instead, you just have them forming. And then you're going to end up in a situation where every water molecule is making its maximum amount of hydrogen bonds, which is 4. And if all the water molecules are making 4 hydrogen bonds, they can only have a particular shape or arrangement vis-a-vis each other if they're going to, be making all of those bonds. So they're going to settle out into this crystal lattice structure. A crystal structure is just a repeating pattern, a repeating structure throughout a substance. And ice is an example of a crystal lattice structure. So all of the water molecules will have a particular arrangement vis-a-vis all the other water molecules around them when they are in ice. And it is the hydrogen bonds between them that is kind of forcing them into that structure and stabilizing it. And then they freeze there, and you end up with a not very dense solid, which is ice. So that's kind of shown in this diagram. Here you have liquid water. The molecules are all moving pretty quickly. They're tumbling past each other. You can't see it very well, of course, because it's kind of confused in here, but they are always making and breaking hydrogen bonds with each other. And it's kind of dense. They're all kind of on top of each other there. As the temperature goes down, they're going to move slower and slower and slower. They're going to make more and more hydrogen bonds. They're going to break less and less hydrogen bonds until they end up, just before freezing, making the maximum amount of hydrogen bonds that they can, which is 4 each. If the water molecules are all making 4 hydrogen bonds each, they're going to have to assume this type of honeycomb-like shape, where you have a water molecule hydrogen bonded to 3 other water molecules around it, and then also hydrogen bonded to 1 in front or behind it. And of course you can see that this is not a very dense structure. It has these giant kind of holes in it, so it's a lot less dense than this, which is just a confused jumble, everything on top of everything. Here you have spaces between all of these molecules. So that is the reason why ice is less dense than water, because of all those spaces. And of course the reason why it's held into this pattern where you end up with all these spaces is because of the hydrogen bonds. If you're going to be making 4 hydrogen bonds with every water molecule, you have to be in this pattern. There's no other way to make that happen. So the fact that ice floats on top of liquid water might not at first glance seem that important for life, because it's not that important for us personally right now. It means that we can have ice floating around and clinking in our glasses, so that's cool, but it's not exactly essential for our life. But there are a lot of life forms for which it is, or for whom it's completely essential. So basically, any organism that lives in a body of water that freezes is going to be relying for its continued life on the fact that ice floats. So because ice floats, that means that the surface of a body of water will freeze, but then the area beneath it isn't going to freeze. So if you have a pond in wintertime, the surface of this water will freeze, the ice will float on top of the pond, and the rest of the pond will be insulated. The rest of the pond is going to end up being warmer than the surface. It is insulated by this level of ice and by this layer of ice, and by the fact that water, is just very hard to change its temperature. So it's going to remain liquid and even a little bit warmer than you might think. And that means that any fishes that are in the pond don't have to die that winter. They get to have, a nice liquid water place to live, which they need. So of course that's not just true for fishes living in ponds, but also for seals and other animals living in the Arctic, such as, whatever this is, some cool looking jellyfish. So let's kind of think about what would happen to a pond if ice didn't float. Well, you would have the top layer freeze over, and then if ice sinks, then that top layer of ice would sink to the bottom of the pond. That would expose a new layer of liquid water at the top, which would freeze over, and then that would sink. Then you would have the next layer freeze over and sink, so on and so forth, until the whole pond is just full of ice. And of course fish and other organisms living in the pond, they can't live in ice. They live in water, not in ice, so they're going to die. Then when the summer comes actually the sun is only going to be able to thaw out the top layer of that water. The rest of it is just going to be ice forever now, because it is so very hard to change the temperature of water. The sun's rays are only going to be able to do it at the top. That energy from the sun is not even going to reach far enough down into the pond to freeze or to thaw out the bottom of the pond. So this would happen to ponds maybe within a single winter if ice didn't float, but it would also actually happen to the ocean eventually. Right, so one year you would have ice form on the surface of the ocean. If ice didn't float, then that would all sink to the bottom of the ocean. The next year, another layer of ice would form, so on and so forth, until eventually you had so many layers of ice down there that it actually filled up the entire ocean, and the whole ocean would just freeze over. Then in the summertime, a little bit of water at the top of the ocean would thaw out, and the rest of it would be frozen still. So if that was the case, then we would not even be here actually, even though we don't live in the ocean, because our ancestors lived in the ocean, right? Like we all come from fish ultimately, and from, single-celled organisms before that. Those are all aquatic organisms. Life kind of began in the oceans as far as we're aware. And certainly, our evolutionary lineage lived in the oceans before it lived on land. So if the oceans were just ice, then there wouldn't be any us. Our ancestors, the fishes, would be dead, and we would never have lived in the first place. And it's actually not even clear if multicellular life would have evolved in the first place either, so there might not even have been fish. Like if you did have life just starting in the ocean with all these single-celled organisms living in the ocean, and then the ocean just freezes, some of them might be able to survive living in the ice. There are actually microorganisms that live in the ice, like bacteria and stuff that live in ice. But, those guys are not going to be evolving to make fish if the environment they live in is nothing but ice. So we definitely would not have existed if ice did not float. So, it ends up being pretty important for us, just not right now. And I think I actually forgot to mention before that water being the universal solvent matters for us because we need it for metabolism. So, your cells are mostly water. They have a bunch of stuff dissolved in that water, and they have a bunch of chemical reactions that they're doing or that are going on inside the cell. All those chemical reactions are the metabolism of the cell. So it's using those reactions to get energy, to build structures, and to do all the processes that it needs for life. In order to have those chemical reactions going on, it's really, 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 really useful if you have the reactants dissolved in some solvent like water. So actually, if you just have, you can actually see this in certain chemical reactions. You might have two substances that will react together, and both of them are kind of in a powder form. So then if you take some of the first powder and put it in a beaker, and then you pour in the second powder on top of it, you know that those two substances are supposed to do a chemical reactions together. But you could actually just sit there and watch the powder and see nothing happening. The chemical reaction just not happening, even though it's supposed to go. And then if you add some water to that beaker, then you'll see things start bubbling and the reactions start to proceed. So reactions will happen way faster if you have a solvent. If the reactants are dissolved in a solvent, that makes things go so much faster. And it's just because you might have two powders that are mingled together, and so for you, it looks like they're close together and they're together, but it might not be that the reactants are actually touching the products in the right way that they need to be in order for the reaction to happen. So if you have everything dissolved in a solvent, everything's tumbling past everything else, things are going to end up hitting each other and coming really close into contact in just the right way that they need in order for a reaction to occur. So the fact that we have a solvent filling up our cells is really necessary for metabolism to take place on a time scale that is relevant to us. We don't want to be waiting there for ages and ages for the reactions that we need to happen. We want them to happen right away. We have to have a solvent in order to do that.